I would like to welcome everyone. So actually, the keynote speech which I'm preparing for today is rather different from what I anticipate I'm going to speak about. I mean, for those who doesn't know about Tanzania, we are undergoing through hard times at the moment. So we are in the mourning position because what happened is we have lost our president, our fifth president, Dr. John Pombe Magufuli. So, I mean, if I were to speak about him in short, I mean, he was a visionary and he's the man who devoted whole of his life to his country and his people. I mean, in one place, I mean, he said, my government will put emphasis on fighting corruption, job creation, and industrialization. I mean, for me, personally speaking, he was a nationalist, he was a Pan-Africanist. I could compare to him like people like Thomas Sankara. You know, he believed that Africa will be built by the Africans themselves. So he never is scared to express his own feelings. Technically, he was never hypocrite. You get what you see. So he's somebody you could trust if if he's your leader. So he's someone you could trust. He was an engineer like us. He led the way by believing in implementation and deliverables. I mean, when he came into power, he sacked over 10,000 people for having fake certificates. And also, he was never a talker. I mean, he was a doer. I mean, he said, I mean, when he came to the power, one of his best quotes, he said, the way to treat a boil is to squeeze it out. And I have made it my responsibility to do that. I know squeezing it out a boil hurts, but unfortunately, there are no two ways out about it. So when he came into power, one of the famous saying in Tanzania was kutumbua majipu. So it's like squeezing a boil. So of course, there are a couple of people, they never like this kind of the approach, but yeah, so it's a big loss for the country, but we have to honor him by taking Tanzania towards the industrialization. So maybe just to give you an insight about who we are as the Tanzania diaspora. So I'll read through to you some of our vision, mission, and objectives, and then we'll make a start. So our vision is participating in enabling Tanzania to realize her full potential through innovation by unleashing our knowledge, skill, expertise acquired from our host countries. So that is our vision. And our mission is to lead in providing excellence engineering and innovation solution to Tanzania industry, inspiring local engineers while facilitating knowledge transfer through professional training of skills and sharing expertise at the global level. So we have several objectives, and one of our first objectives is to actively collaborate with Tanzania industry to deliver high quality and standard projects or products, to formulate and run new projects, and actively collaborate with Tanzania industry in research and development. Also to directly bridge the knowledge gap, as we know that most of us, we are in host countries, and most of the host countries are developed countries. So we want to pass this kind of knowledge transfer and to fill the gap to our home countries. Also, we want to provide high quality and high standard training to Tanzania engineers through special programs. So it could be through short course, seminars, virtual training, and conferences like the ones we are doing today. In the future as well, we are looking forward to provide scholarship to pursue further education for selected students, as well as supporting professional development of our member countries. Our members, yeah, any person who is a member of Tanzania Diaspora. We are looking forward, I mean, once we are fully established, to be able to provide some sort of professional support, as well as to provide certification to our members on basis of their professional practice. And also lastly, to collaborate with Tanzania professional institutions such as Board of Engineers, government regulators, to ensure continuing of good engineering practice. So, I mean, at the moment, the group is made of over 110 engineers, of whom we are located in different, some people are in Japan. I could see Osman Mwambe, he pursuing his PhD. You have some people in Turkey, Some of us are based in the United Kingdom. You got people in Uganda, Kenya, all over the place. So we group us together, join our skills and expertise, and the objective is to transform that back home, and so that the benefit, the Tanzania can see the benefit of diaspora. Having said that, so without further delay, so I would like to welcome our first guest speaker. He will introduce himself, but for me, he's my friend, he's a brother, Dr. Umut Genj. So he will speak about self-driving cars, and he's leading on that domain. So you will hear a lot more from him. Welcome, Umut.
Okay, thank you, Otman. Thank you for the nice introduction. Well, hi everyone. I mean, thanks for also, welcoming me here. I always, love being with engineers. That was also my personal passion, engineering and science. We also do similar things, or I mean, when I was a bit younger, I used to do more. Now with kids, it's more difficult, but we used to also do, Turkish engineering diaspora meetings. So I definitely support the initiative and wish everyone, I think, best luck and good productive discussions, because together we are stronger. That's always true for any kind of, groups. So I think that's very useful. With that, my background. So yeah, I'm from Turkey, electrical electronics guy. ODTÜ graduate from Ankara, for those who knows this Ankara University. Then I got scholarship to Manchester, then Cambridge. But of course, I'm a bit older now. This is all 90s. So I finished my PhD in 2002 from Cambridge. And after that, I joined Automotive Industry. Always work for German automotive companies. I still know exactly why always Germans hired me, but I never worked for any other, company apart from the Germanic ones.
And which exactly? Sorry.
Like, well, several of them, but the first one was D-Space. Okay. Then IAV from Gifhorn, it's 50% VW owned, and then AVL, which is a very large Austrian one. So I was at AVL for 13 years. Last 10 years, I was a managing director in AVL in Turkey.
Okay.
And in 2018, I was looking for trouble probably. I said, okay, that's enough corporate life, and, convinced two of my managers, and we started a startup. That was, 3 years ago, to focus on software development for battery management and also semi-autonomous driving, advanced driver assistance systems, doing autopilot. So we are a software company combining AI machine learning with automotive software development processes. And the idea is really to supply intelligent software for automotive production applications, and production part is key, because a lot of what we see on YouTube, on the news, is demonstration projects. And any good engineers, you bring 5-10 good engineers together, you make a demonstration. Even flying car, I mean, give us $5 million. Really, all of us here, we make a flying car. But you make one car which flies on a sunny day, up to 5 meters, and that's it. And so the trick is, to make a real product, which means could work in any continent, when it's hot, when it is cold, when it's raining, when it's foggy. And that's the difficult part, and that's our mission, make real products that can go into production. But with that now, let me go to my presentation, because in the presentation, I want to talk about autonomous driving. I will look at the history of autonomous driving, how it developed, and focus on the last 10 years, and why we also still cannot buy an autonomous driving car, right? I mean, there are a lot of all these promises and everything, and I'll show you. But really, you cannot go and, I mean, the best thing you can buy is a Tesla. But a Tesla is really, it's not really autonomous. I mean, we all know that. And if you are not careful, you end up with an accident. So, presentation mode. So I assume you can see my screen.
Yeah.
Good. Okay. So I already introduced the title. So very quickly, I will remind you levels of autonomy. That's important if you know it. Sorry about boring you, but if you don't know it, there are 5 levels of autonomy, from level 1 to level 5. Level 1 is just assisting the driver either by controlling steering, right? Software either controls steering or it controls braking and gas acceleration, but you don't control both. For example, adaptive cruise control is an example of level 1 autonomy or level 1 ADAS. Then you have level 2. In the level 2, both steering and acceleration, meaning braking and gas, are controlled by software. That's good. But as the driver, you still have to keep your attention on the road. So you cannot play with your mobile phone. You cannot read a book or something. So level 2 is usually what we get in an expensive car today. Yeah, if you buy a cutting edge good BMW, or if you have a Tesla, you have this level 2. That means car can really do a lot of the driving, on the highway. You don't have to touch the steering and all that. But still, you have to watch carefully all the time, and you need to intervene if you see something is happening, right? Dangerous, something is unusual, you are responsible. This is level 2. And it gets really interesting when you go above level 2, starting with level 3. Level 3, in terms of what software could do, is same as level 2. So software controls steering and acceleration, braking. But you don't have to watch the road all the time or look at the traffic all the time. So when it is level 3, you can actually play with your mobile phone. But your ear has to be with the car. So if you hear a warning signal, or if you hear a buzz or some warning from the vehicle at level 3, usually you have 1 or 2 minutes, sometimes even less than a minute, to take back the control. That's level 3. And as of today, there is only one company, whole world, officially selling level 3, just to give you the feeling. Again, when you go YouTube, you see a lot of these robot cars and blah, blah, but if you want to buy, there is only one company, and I'll tell you more later on, that's Honda in Japan. And they only start selling level 3 last week. It's only just started. And even if you go details, then you see that actually they only lease them, and only 100 units at the moment. So very, very careful. Even level 3 is very careful. When you go level 4, that means actually you can watch a movie. You don't even, wait for the warning. So level 4 is what we call driverless car, or what we call a robotaxi. That's level 4. And there are a lot of high or celebrity startups in US, doing this level 4 application, like Waymo's and Cruise, and they try to do these robotaxi applications. That's where level 4. And at the moment, they can only do demonstration. And level 5 is basically level 4, but anytime, anywhere. So level 4 means, for example, you could be in the central London and you can have some robotaxis specifically trained, learned central London. So they operate in central London. But if you take them to, let's say, Birmingham, they wouldn't work. That's level 4. So in certain areas, you have this driverless cars. That's level 4. Level 5 is an idealization. That means anywhere, anytime, full autonomy, driverless. And I don't believe that. Again, we are all very international here. You can have a nice autonomous car in Europe, and I'm sure if you take it to Tanzania, it's not going to work. So that's why this level 5 doesn't make sense to me. We are all engineers, but level 4 is already very, very difficult. So this is the important, levels of autonomy, and then this will be, please try to remember it. But let's look at very quickly the history of this self-driving cars. Of course, there's history. This picture is from 1950s from US. So even in 50s, there were already, some advertisements, some marketing material talking about automated highways, electric cars controlled by computers. There is a video I tried to share. Let me turn it off. But this is an advertisement from Firebird from GM. And in this video, basically what's happening, this family is traveling from A to B in the United States. And there, there's like a control tower. So the vision is similar to airports, to planes. And they're saying this control tower, hey, tower, we want to go to, I don't know, to San Francisco, how we can go, is there is the automated highways available, and talking to this tower, and then they will go to this automated lane and it will take you there. So kind of a vision, but again, this is from 50s. So this dream about driverless cars, autonomous driving is old, it's not new. And there were already some mechanical applications for fixing the cruise speed. Yeah, so cruise control CC was already available in mechanical forms even before. And the first electrical one was from 58 with Chrysler. This was the first electrical cruise control. And this is level 1 autonomy, right? It's just controlling the speed. And then very quickly, again, history of this autonomy or driver assistance systems, ADAS, Advanced Driver Assistance Systems. ABS actually starts from 70s. Of course, I'm also Turkish. I mean, they say 70s, but in Turkey, I think you wouldn't get ABS until mid-90s. So a lot of the things you see here, like the first very expensive cars, yeah, Mercedes, BMW, they have it. But when it becomes, commonly available, it's much later on. But nowadays, all of us, when you buy a modern car, there's always emergency braking. Semi-automated park assist is very, very common. Lane keeping, some, blind spot monitoring with premium cars. So these are all available level 1, mostly level 1 features. Because level 2 is more advanced. Again, Tesla Autopilot is level 2. Yeah, both steering and acceleration braking done by the software. But only very premium cars have level 2, or sometimes we call level 2 plus. Then I want to now come back a bit 2015-16, and there were big promises around self-driving cars and level 4 autonomy. And let's look at some headlines. And I think you all know Elon Musk. Mostly we like him because he's a really good, I think, visionary and good engineer, scientist. But he claimed, and this is in 2016, in 2016 he said, in 2017, Tesla will go from one end of United States to another one autonomously. And I think we all know that didn't happen. It's also didn't happen today. Then another headline from 2016, Ford says, yeah, no problem. In 2021, we will mass produce, right? Not just mass produce autonomous cars. And please let me know if you can buy any autonomous car from Ford today. Mercedes, they did the same. I mean, names are irrelevant. Yeah, they were all doing that. Toyota, GM. So everybody claimed, 5 years ago, yeah, we got it, autonomous cars. And then it didn't happen. And the rest of the presentation, I will just highlight why it didn't happen and then what we can expect. And to understand why it didn't happen, I want to introduce this a good model from a company called Gartner. Gartner is a consultancy like McKinsey's, Accenture's. And they have a model called Gartner Hype Cycle. And I actually recommend you all look into that one because it's a good model to understand emerging technologies. So if you're interested in, what is coming up, if you are following the latest tech, this is a really good model. So it has 2 dimensions. The vertical one is about expectation, so emotion, the excitement dimension. And on the horizontal line, you see stages of new technology, emerging technology. So in the beginning, you have innovation triggers. Yeah, some enablers that kind of starts or convinces people that this new technology is possible, and the excitement goes up. Yeah, this is the excitement. And then the next stage is you got over excitement. Here you peak. Yeah, inflated expectations. And this is kind of the headlines I show you. Everybody thinks, oh, it's happening. Yeah. Okay, tomorrow I can buy this robot car. Oh, this flying car, quantum computing, AI will take over the world. Yeah. So so this is that part. And then usually what happens, and a lot of the case, that's what happens. Suddenly it picks up and people realize, oops, sorry, mate, it's not happening. Oh, it's not happening. And a lot of people might lose money if you are in the investment business in stocks. Then you might, and this is the disillusionment part, yeah. So this is kind of the frustration. And very few of the technology continues, and then this is called slope of enlightenment. And this is the usual development of the technology. Yeah, slowly it matures up, and then we can buy driverless cars. So this is a good model, and you can apply to quantum computing. Yeah, you can apply to autonomous cars. any kind of emerging technology you can apply. But important, not every technology will make to this enlightenment level. A lot of them get stuck around here. Yeah. So let's look at some innovation triggers for self-driving cars. And I believe this is my personal view, but it was between 2004 and 2014. So the first one was Darpa challenges from United States. And you can check on Wikipedia. These were very specific competition by this Darpa, the Defense Department of United States. And they were inviting university students, university teams, to this competition in desert to get an autonomous car to go, by itself, roughly 200 miles from A to B on a desert environment. And the rewards were really high. I think that's one of the good, or not a good thing, but maybe why US is strong in technology, because the winning team was getting $2 million. That's a lot of money. I mean, in a lot of other countries, what you give, maybe $50,000 to a student, team. No, in the US, this was, if you win that race, you get $2 million, a lot of money. So they did that in 2004, and there was no winners. And then they repeated it in 2005, and then there were 13 winners, in 1 year. A lot of teams won. And the last one they did in 2007, and that was city center autonomous challenge, so in an urban environment. And again, there were 2 winners. But what that happened, actually, a lot of students who joined this DARPA challenges from different universities in the US, now they are leading all these autonomous driving startups in Silicon Valley. So it created the human capital. So they all become founders, CTOs, CEOs of all these new companies. The next one is the reborn of the AI. And this is the Imagenet challenge. This is basically about, the image recognition. So using software to detect objects, if it is a cat, if it is a bus, if it is a bicycle, if it's a dog, pedestrian. And this is another challenge. It's done yearly. This bar shows you each year. It starts from 2010, and this one shows until 2015. The winning software. So this is for software. Sorry. Can you hear me, guys?
Yeah.
Yes.
Yes.
Okay. Because it says it's unmuted. Sorry, that was something. But basically, you can see that in 2010, the winning software, it won by making 28% mistake. This is the mistakes, actually, misdetections of objects, 28%. So this is the 2010 winner, 2011 winner. And in 2012, the winning software was a neural network called CNN, convolutional neural network. And it really, it won by only 16% margin. And later on, every year, all the winning software is another neural network. And in 2015, the error was only 3.6%. And this is as good as human. So you can see that suddenly the perception, the vision algorithms improved a lot. Another big enabler for autonomous driving. Then, of course, you need a lot of money, venture capital. You cannot see that this is small, but you can check it. The amount of venture capital money going into autonomous driving really picked up since 2010. And the last one is computers, computing power. We all know about this Moore's law. So we double the number of transistors every 2 years on a microchip. And actually, this trend still continues since 1970s. It's unbelievable. And today, if you buy a cutting-edge NVIDIA chip or AMD chip, Intel chip, it has 50 billion transistors on it. Not 50 million, 50 billion. On that little chip. It's unbelievable. But all this together, right, these are the innovation triggers. All of them make this excitement, this journey for self-driving cars possible. And people put all that money in, and all that excitement started, right, in our model. And then we got this, over-excitement, inflated expectations. So we're in the second stage. And this is the part I already told, I will not repeat. Everybody said, yes, we got it now. Autonomous cars are coming. Level 4 is coming. And then let's go to the next one. And then we come to this valley of disillusionment. Yeah, so we are in this now stage third. The first bad news were from Uber. We all know Uber, and they had an accident. I'm sure you remember in 2018. Unfortunately, they killed an unlucky woman on the road during testing, and that made big news. And a lot of self-driving startups and tests were stopped. For example, Toyota immediately stopped its testing after this crash. GM said, GM Cruise is the main startup of General Motors. So they said they're gonna delay their testing, autonomous rideshare. And suddenly Toyota said, well, maybe, we were a bit exaggerating, there was overhype. Daimler said, remember in the previous slide, they were making all this robotaxi, they said, let's do a reality check. Ford clearly understand, I'm sure they knew even from the beginning, but this 2021 target was not realistic. Then there were more headlines, surprise, surprise, nothing is happening in 2020. This is from last year. And so suddenly we were in this trough of disillusionment. People realize this will not happen. And one slide, why, since we are all engineers, why it's so difficult to make level 4 autonomy, driverless cars. Number one reason is safety. Driving a car is not like a mobile phone. It's similar to flying a plane. And we all fly from time to time. I'm sure now we all miss it. Yes, because of COVID, we are not flying much. But you realize there's a lot of automation in planes. There's autopilot in planes for many years. But we all know that there are still at least 2 pilots. Why we cannot get rid of the pilots? Because again, flying, driving, we carry people, we carry lives. So it's a very, very critical application. And you need a lot of testing, certification to get any kind of autonomy in driving as well as flying. So perception is still difficult. We achieve 97%, 98% quality in perception, but even 2% when you are talking about self-driving robot cars is very high, right? There are so many cars, almost 1 billion cars, 2% means, 2 million accidents. So you cannot have this, so you need to still improve the perception. The other one is prediction, meaning you have the car in traffic and you need to predict other cars, other buses, other agents in traffic, right? If you see a cyclist, if this cyclist will jump onto the road, or you see a person, we are all, again, I'm Turkish, you're from Tanzania, sometimes we communicate with eyes, I look at this person and I know if this person will jump onto the road or will wait for me, right, with the eye. And of course, this AI machine learning, and I assure you, there's no real intelligence. They cannot learn this. It's so difficult just looking at the eyes and communicating. So this prediction is still not good enough. And the last one is, how do we test all this autonomous software? It's so complex. Doing the verification, validation, and again, like Otman, like Mustafa, you are all working for JLR. This is a very, very tedious, rigorous process, and it is not simple to test this kind of complex software for automotive. So these are all around safety. Then we have cost problem. All these cars have so many sensors. We have cameras and multiple cameras. We have multiple radars. Then anything beyond level 3, we have to put LiDAR. We have to put very expensive compute units. Then we need to upgrade the electrical architecture because a typical 12-volt, 24-volt battery cannot support this very, very, intensive computational electronics we got. So such cars are very expensive today. So we can, even if we get the safety, we cannot still sell them on a normal price level. And the last one is legislation. You need to also make sure that the lawmakers are, upgrade all the new laws. There's the new regulations, because today it's honestly illegal to read a book or watch a movie when you are driving a car, right? Even if technology is there. So a lot of reasons why we couldn't see self-driving cars in 2021. Okay, last 5 minutes. But there are good news. So people realize that this will not happen in the short term. But I can tell you that we are now in the enlightenment phase. So slowly we are getting there. My view is we will reach there in 5 to 10 years. So hopefully we will all see. So now Waymo is doing completely driverless taxi service in a small town in US, Phoenix. But it's a very ideal place, right? There's no rain, full sunshine. And I looked at some of the videos. You don't see any dogs, any cats on the street. I mean, it's like SimCity. So, but they have this now, even without safety drivers. So they have that. Cruise, again, trying to do some driverless testing in San Francisco without the safety driver. That's important. No, so not even a safety person in the car. Then Hyundai Optiv is trying. Yandex, the Russians, they are doing some trials in Las Vegas. Then Microsoft invests a lot of money in Cruise. Tesla gets about to get permission in Germany for level 4. And the last one is Honda, we already discussed. So Honda starts selling this level 3 in Japan. But as I told you, it's very limited sales. Actually, they don't really sell, only 100 units. They lease it for specific customers only in Japan. So what is my personal expectation? Well, I see that on the highways, we will see level 4, this driverless, the first application will be on highways, and traffic jam assist, TGA is traffic jam. It's easier to do. But I see that by 2025, we will have, or some cars, lucky ones with enough money, premium cars, will have this highway automation and traffic jam assist. Then in campuses, airports, big hospitals, we will have autonomous shuttles. Then low-speed applications for level 4, so autonomous delivery, for example. So you can have these robots delivering pizzas at low speed in city centers. And of course, robotaxis. We will see that in certain areas. And my last thing is, I want to show you our work at e-tron. So you see that our highway testing in Istanbul, right? This is with our highway pilot. And on the right-hand side, you see our track testing in the UK. So also as e-tron, we got driverless software stack. So this is level 2+, including full automated lane change. So we are doing a lot of highway testing in Istanbul, which is a good area. But also on the right-hand side, we are doing a lot of official testing, ADAS testing, NCAP testing in the UK. So, and thank you.
Thank you very much, Dr. Umut. So I think,
no problem.
Yeah, we're gonna move to the.
I don't know if you have time for questions.
Yeah, so we will take like maybe 3 questions just because of the time. So anyone who has got question to Umut, please. So we're just gonna take only 3 questions because of the time. Please open up your microphone and fire the question to Umut. I think he's ready to take it. Otherwise, I will start myself. I had one question really, Umut. I mean, it was mainly on the cybersecurity. I mean, you mentioned
I
about
wanted to ask the same thing. Okay, go ahead.
Yeah, Umut, it seems like you have some connection problem, isn't it? Yeah, I think it seems to be frozen.
No, I'm back now. Sorry.
You're back now. Yeah, okay.
My Zoom crashed.
Okay. Yeah. So I think my first question was really based on the safety and the cybersecurity, because you mentioned about the safety for perception, prediction, the validation. So I was mainly concerned about how is the cybersecurity, as we know that the terrorists will be ready to take over, especially in this kind of scenario. I mean,
no, I agree. Cybersecurity is another concern, and we don't have such expertise at e-tron in-house, but we work with partners, other expert companies on cybersecurity. And I clearly agree, Otman, cybersecurity is another big concern, because even with level 2, as you said, with some people with bad intentions, they can get you into a crash, right?
Yeah.
I mean, level 4, we don't have it today, so they cannot really kidnap you. But if they play with your acceleration braking, so they can get you hit someone else. And so, no, I agree. But this is a big topic, and it's part of the certification. So you need to also get the cybersecurity certification. But for anything beyond level 2, level 3, and level 4, I fully agree. There's a big concern. And sometimes, as you said, some terrorist, but even it could be some, a bit heavy-handed government can also kidnap people while you think you are going, commuting to home or work. So it's, I think, a risky technology.
Yeah. Any other question?
Yeah, just a quick one. Yeah, thanks for the presentation. It's very, very, very good. In one of the earlier videos you showed about, I think that was in the early 1950s, where was that Ford? So where they were driving and then they were speaking to some tower to understand where to some highway parts that they could use. Yeah. So in today's application, yeah, when you need two cars to communicate car-to-car communication, I believe there would be a lot of smart grid, smart motorways, and all of those. So how is your company and companies that are actively involved in this sort of research? What sort of technology do we expect to see in the near future that would enable? I know there's 5G now, but we expect to see more technologies emerge to enable this.
No, I think a very good question. This is more called in the area of connected cars. You're right. And it's a very active area of research. As e-tron, in our startup, we don't do connectivity. But I can tell you that if you want to secure safety of especially level 4, right, driverless cars, you definitely have to have this connectivity, vehicle to vehicle, vehicle to infrastructure. So that will play a key role to make sure that you can have improved performance and also safety in complex driving situations. So that's and there's a lot of work in that area, but we don't do that at e-tron. But connectivity is I think is a big player. The other thing is this control tower example was a good one. For level 4 and even for level 3, one of the backup solutions for safety is we call it teleoperation. So actually you will have some operators who could intervene and drive the car remotely if some emergency happens in the car, right? Let's say suddenly you lost one sensor, or let's say the driver had a heart attack. So there are applications that then some operators could take the control and get the car to a safety, maybe to safety line by remote control, teleoperation. And that's part of the connectivity. So that's also, I think, a very active area of research, both for autonomous driving, but also for autonomous delivery. A lot of these small robots you see that people are trying on the road, right? I think there are some also around Milton Keynes delivering small goods. They all have teleoperation enabled. So when robots get stuck, somebody in front of a computer, like playing a computer game, sees what's happening with the joystick and tell robot, okay, go around that, whatever, this obstacle. So that connectivity and teleoperation is a big part of the future of autonomous driving.
Yeah, that's a good one. So we take the last one for Dr. Umut, and then we move to the next topic.
I would like to ask a question. How are you dealing with the legislation? Because I think this is a big topic, isn't it? I mean,
yes.
If you drive in your car, let's say you have a choice. If you have an accident, you have a choice to either save a human, to be able to save maybe cyclists, or what? How this kind of decision are you trying to take if you need to consider the legislation? I think this is a big topic which are kind of I don't know, halting, I would say, the autonomous driving, isn't it? How are you dealing that, the legislation?
I mean, at the moment for us, again, at e-tron, actually, we don't develop such software functions.
Okay.
So our software is weak because, as you said, you are fully right, because this is a very controversial topic, ethics, philosophy. And so we like to stick to the engineering. Usually our algorithms work like what is the, the shortest distance, the minimum impact I can achieve. So we try to optimize a mathematical function rather than saying that should I hit, a pedestrian, or so we try to go for the minimum damage, stopping. That's the idea. Anything beyond, then we would ask the regulators. So as engineers, normally we don't make such decisions, Adama, because as you said, it's dangerous.
Right.
So either we put a mathematical formula, minimum distance, minimum impact, and then the optimization algorithm decides what happens. We don't want to know that there's a decision about, old person, young person. But anything beyond, then we would ask lawmakers, legislators. But trust me, they are making that. So they are not finalized yet, but in the UN, there are work groups in United Nations. They create such regulations for all the manufacturers and engineering companies.
Right.
So there will be regulations coming, and they will tell us how to develop this kind of sensitive software.
Right.
Yeah.
Okay. Thanks.
If I can add something there. I think I'm not sure who exactly is normally involved in these discussions when it comes to legislation, because I think there is an importance that I think it's very important that people who really have the knowledge, for example, engineers like you, Dr. Umut, to also get involved in these discussions, because most of the time you would find that it's maybe the lawyers who are trying to understand how these things work, and then they come up with all these regulations without really deeply understanding how autonomous driving works, for example, or how vehicle-to-vehicle technology works. So they just use their understanding to come up with these rules and regulations. So I think it's time that we as engineers really get involved into these discussions, because sometimes when you look at when one Tesla car, for example, gets into an accident because the driver was, I don't know, reading a newspaper and put it on autopilot, it makes big news.
Yes.
But the reality is, so far, we see that actually software and AI is more efficient in some cases than the humans, because when you look at the number of accidents, when you look at the statistics, every day so many people die because of accidents, So these are things that really need to be taken into consideration. So it's time that we as engineers got involved in all these panels and discussions, not to leave it in the hands of people who don't really have a good and a deep understanding of how these complex systems work.
No, I agree, Kasim. I mean, but it's not easy, as you know. I mean, we are good in maths and algorithms, and when you go in front of a lawyer, usually they speak, at least they definitely speak better than I do. And so we need more support. The other one is the public perception. I mean, we know it again from planes. When there's even one plane accident, it becomes a big news. So people are very sensitive. So when one of us makes an accident, a human makes an accident, it's not news at all. But as soon as a software makes an accident, even one, as you say, it's big news. So people are very sensitive about this high technology. And I agree with you. So it's a bit unfair. So they want a perfection. But actually, even today's, I think, level is safer than a typical human driver. But this is not good enough for public opinion, unfortunately.
So thank you very much, Dr. Umut. I think it was eye-opening discussion, and I'm sure there's a lot of engineers who are already in that area. So we're gonna cross over again. So the next topic is introduction of Internet of Things, and it's going to be presented to you by Otmar Mwambe. So it's PhD students from Japan. Please, Otmar Mwambe, welcome.
I think can you unmute?
Hello everyone. Sorry, I was muted. I forgot that I was muted. I'm Otsumari from Japan. May I share my screen?
Yeah, sure.
Okay, just a second. Yes, can you see my screen?
Yes,
Yeah.
exactly.
Yes.
All right. So today, first of all, I should pass my condolences to the Tanzanians that we have lost our president. We are now at the period of mourning. Yeah, we are all very sad for the passing of our president that they are now in the process of the barrier. So I'm very sorry for Tanzanians. And for me, thank you, Dr. Omut, for the automobile. Actually, I just saw the car 2 days ago here in Japan, and I was very excited. And some engineers there passing around, they were doing some demonstrations. I was very excited. And today I've got a lot of insights. I never knew the technological situation behind the automation. For today, for me, I'm going to talk very introductory part for the Internet of Things. I should introduce myself. My name is Otmar, as Maganga said, and I live in Japan. Currently, I'm a PhD student at Shibaura Institute of Technology. So I'm the one who's going to talk about the Internet of Things. Briefly, I will introduce the ubiquitous computing era and how the transformation went through from ubiquitous computing to the Internet of Things. Then I will introduce the Internet of Things itself and its applications, some architectures, and the technology that enabling the Internet of Things. And I also discuss the challenges behind the IoT. I really like this picture. From this picture, as you can see, the people, they are very excited. It seems that there was something like really exciting that the people are really into it. They pay all attention. But if you see the arrow pointing at that old lady there, she's very calm. And if you compare that, these young, the millennials, the young people who are really excited with smartphones and whatever, actually they are really distracted using their smartphones. But the old lady there, she's very calm and she's enjoying the event very much. She's very attentive if you compare with other people in the background. But why? Because this old lady, actually, her glasses, they are the glasses, they have embedded the camera, which is capturing the event and the image, and it's also zooming automatically, and she's really enjoying it very clearly. So the image is captured by the glasses. She doesn't need to move. She's not distracted, and automatically it's uploaded to the cloud environment. So that is the technology. That's what we call ubiquitous. That's what we call ubiquitous computing. That we are trying to, ubiquitous computing is trying to not to cause distraction to the users, that they are enjoying the technology, they are using it, they are utilizing the technology, but you don't feel that you are using it. So that's the concept. So we are enhancing the concept is to enhance the computer availability, that we are using it everywhere, but we don't feel it actually. Same as these people, that these people are really with their phones, taking pictures. Actually, the technology is distracting them. So instead of focusing on the events that is happening, they're focusing on the use of what? Mobile phones and whatever to capture the events, which is not necessary for them. So how that happened? Actually, let's talk about the ubiquitous computing, how this started. The ubiquitous computing concept actually started with our normal daily life, that we know that we are surrounded by physical objects. We have houses, we have computers, we have mobile phones, we have a lot of cars, etc., television, so many things. So how do we get control all these physical objects? Is really challenging. A human cannot handle it or handle all of them at the same time. So what is happening now? We need to have control of all these physical objects, but without being distracted. Is when the concept of ubiquitous computing coming in. That how can we enable now the computer to help us having control of all these physical objects without having that burden in our head. So there the concept of ubiquitous computing is coming. So it's trying to abstract this computation of actual physical things. So how this is happening is that we are creating invisible computer. That's the purpose for ubiquitous computing, is create invisible computer. So we have the computation power, which is helping us to handle all these physical objects and reduce that workload on us, and then we are enjoying the technology behind the scene. So that's the purpose. So how comes now we have these mobile phones and smartphones or these iPads? So what do they really do? They connect all these physical objects, and we are able to enjoy having contacts, communicating with all these devices and all physical objects without really paying attention to them. So that's the idea behind the this concept. So what makes this computation capability possible? Actually, the idea, the target, the goal of this ubiquitous computing is to expand human consciousness and to make the context aware and responsive environment, to make our environment interactive, but actually we improve the context awareness. And also to improve human world interaction and improving the computation power performance itself. That's the idea of ubiquitous computing. So let's see the transformation. How did we move to the other, to the current situation? So what is this IoT actually itself? I can tell that previously it started like Internet of people. That people, we have the computer now, everyone is excited. So when I make computer, access the internet, we enjoy, communicate. But it was more human to human, user on internet, enjoying the service. That's how it started. And we really enjoyed in the beginning. And later, things turned. Technology advancement, it became Internet of Things. What happened? The computer itself actually enabled us to sustain the communication between one person and another. But things change now. The game has changed. The computer is given more power. So what we do now, we are no longer communicating with the computer, we're no longer communicating with others, but the target is not only the communication, but now the target is machines communicating with another machine. So the machines, they are communicating themselves. So that's the idea behind the Internet of Things. So if you see now, you see all these actuators, sensors, and whatever, several devices, but actually connected them or not on interconnected networks. So the Internet of Things now, we have given a computer power, additional tasks that should not only do the communication purpose, but we have introduced things. Most of them are sensors, as the previous presenter said. And another thing that is very important, that we have given the computer senses, ability to sense. Like a human, how do we connect to the environment? Actually, we connect ourselves to our environment through 5 senses. This is a normal human being, that we do have the ability to see, we have ability to hear things, and we have ability to smell, to detect smell, to taste and touch. So how do we give a computer that ability? We can only give computer such abilities through sensing, giving it ability to sense. That's why we are using sensors. So in the Internet of Things, to give this computer system such abilities, we are using sensors. Then after that invention, now we get now into the Internet of Things. So this Internet of Things is actually founded by, it's under whatever the foundation of it is on ubiquitous computing. So it adapts all ubiquitous computing characteristics into it. So actually it's a systematic means that we have a worldwide network that is giving these interconnected objects, these sensors, ability to communicate or to sustain, to enable these users to enjoy the environment, computing environment, without even noticing it. Yes, that's the purpose. And through it, when we add these sensors, now we have more objects, we have more sensors, we have more these actuators. So they all have to make communication and data exchange. So here comes an example that how about these people connected with these things? How do humans now, the users, how do they get connected to the things? So before, users only use a computer to communicate because the purpose was human to computer interaction. But now things have changed, the game has changed. Now people are connected with things. What are these things? As I said earlier, these are sensors that we have given the computer systems ability to have senses like humans. So there are several types of sensors nowadays. People are using like on mobile phones. Some they're using their heart, like ECG. Some they use also motion sensor, like these disabled people. But all these sensors, actually, they're all connected on the internet. They are connected on the internet, and these are the ones that are giving this person. It doesn't feel the burden. It doesn't even feel that is controlled by the sensors, but automatically these sensors, they give him ability. So this is what we call things connecting with things, like Dr. Omut just finished here. We just introduced the issue of the car. These smart cars that are fully automated that we are hoping that in the 10 years to have. So if that car will probably come, then is part of what? Is part of the Internet of Things that you can see the structure showed that the car is full of sensors. So all those are the objects that are connected. This is what we call things. Some complex systems now, they are all connected through what? Through internet. So what happened actually in the transformation, the technical whatever evolution? In the beginning, long time ago, we were talking about human to human communication before even we had this World Wide Web. But things changed. That time, people used technology for communication, like these mobile phones. We are just using for SMS most of the time. And there, the most important thing was only phone, that you can only talk, we can make the verbal communication and SMS. That was like, they saw it like really highly advanced technology. And later game changed when the introduction of what? World Wide Web. Things changed. And then we had email. Information became like what? Having easy access to the information. And we got more entertained. And things changed when they advanced this World Wide Web. When we invented the Web 2 technology, then things changed. People, they commercialize the website. So this web architecture, now they commercialize it, and we started having the e-commerce like Amazon and some sort of. So then the phone was no longer the phone. It was smartphones, and we started having some applications, using some applications. And then things changed later when they introduced now the internet of people, is when people started using and get influenced by the social media, Skype, Facebook, and some YouTube, people having entertainment. So this is the time when this phase for the what? Internet of people. And currently things have changed. They've gone even further, that we have now Internet of Things. Now we talk about machine connecting to machine. Sensors, they talk to themselves, they talk to one another. And we are not aware of it at all, but we're just enjoying the computation power. So this is what happened. That's the evolution that happened in the technology. So what happened to this Internet of Things? What is behind it actually? Actually, it's playing part at the communication layer. I hope there are people here who are networking specialists. They should know the cyber physical system that we are usually using for communication. So the IoT itself is just playing here at the communication layer, that we have the application layer and we have these actuators, these sensors, but itself is just playing the what? With the communication layer, where it's giving the data, it's giving ability for what? For data transfer and sharing of what? of this data from the sensors to the application layer. That's what Internet of Things does. So how can you differentiate? How can you compare this now Internet of Things and this normal physical system? Actually, they're pretty similar, but slightly different. That this physical system, they act separate. But the Internet of Things is a networking infrastructure because it's only dealing with what? With the communication layer. And if you see the objective, this one is interconnected to various networks because it's connecting devices, computer and computer, machine and machine. Not like the objective of the what? Normal physical system. And for the architecture, we found like this more vertical architecture, while the Internet of Things is more likely to be horizontal architecture. So, why is it a big deal? Why do we need this very much? And why do people really talk about this Internet of Things? What the potential? It's very useful and it's very crucial. Why? Because it has improved computation performance. The computer does more than we expected at the moment, and it has enabled cost reduction. It has saved a lot because now we are able to we don't need to buy several computer chips. We don't have to buy computers a lot. We don't have to buy even a lot of softwares. We can have access to all the softwares on the cloud environment. We can have access to all facilities. You don't need to install even Microsoft Word in your computer any longer. You can access this service on cloud. Yes, that's the benefit. And also it has increased creative innovation services. That's why you see now there's several types of applications, and every day new ones are coming out. So that is part of what this Internet of Things. And that way it has increased the revenue because many people now, big investors are now putting money into what? Into it, and now it's becoming really commercialized. And as I said before, that what we can see now, we have now smart houses that they're always, we call them smart houses. These are fully automated. I don't know the level, like Dr. Umut said, for the car. I'm not sure it's level 4 or whatever, but these are what? In developing countries, obviously they're experiencing this situation now. That some of our houses are semi-automated, but in some developed countries, the houses are fully automated, they're full of sensors, and you don't feel to need the control over these sensors. Why? Because you only need a smartphone or a tablet to manage the entire house. So that's what we call it. That's why we call this a smart house. It's part of what? Application of Internet of Things. And now it gives us, we call it a smart egg trays. You just use mobile phone and you have control over it. And also smart lighting and some smart sleep systems and some weather station. Now they're using what? This Internet of Things technology. Also smart garbage cans. Now they're using it in Europe already. And we also have the smart gardening, that watering the flowers. You don't even need to think about it. You just put the water somewhere in the sip tank, and then the automatically to detect, the sensor will detect and to water the flowers. And the architecture behind this, the Internet of Things actually is using 3-layer architecture. As I said earlier, that is usually connecting this application and the perception, the sensors. So for the application layer is where we have these smart houses, these normal applications that have been developed, like whichever you are using. You may have your phone and use some application to access Amazon, whichever. These are at application layer. But how do we perceive this Internet of Things? Actually, they are here themselves, the sensors, at the perception, because we use them for what? For sensing and the network. So we call this a 3-layer architecture. It's very beneficial and very useful. And for Internet of Things is structured in the service-oriented architecture. The idea is to deliver service to people, and that's why they're commercializing. So we have the application layer, which is delivering those applications that we are using currently. And we have a service layer where we see now composition of what? Management of some interfaces. And also we have the network layer that is responsible now for connectivity and perception is where the sensors we are talking about. So it's more service oriented. That's why they commercialize it. And this is a good example that at the application layer, we have several applications that have been integrated. That's why you don't see sometimes that you just use your mobile phone. For instance, in Tanzania, when I went there, it's pretty awesome that you use your mobile phone, you are able to access my bank account. I'm able to send money to mobile M-Pesa. I'm able to communicate. It's very, very interesting. But actually, these applications are integrated. That you see the mobile phone company has been integrated with what?
They have already started.
With the banking system, but we don't feel it. So the user just feeling that we're using a mobile phone, sending money, doing like this. But actually, there are several applications and software that have been integrated. And we also have this information processing. Why do we have this information processing? As I said now that as long as we have these smart systems, the number of these Internet of Things, the number of objects have increased. We have several sensors at the moment. So all these sensors, they send data. They create and send data. It depends on the user interactivity. So what happens now, that's why we talk about big data. As long as these objects have increased dramatically, so we have a challenge on information processing, that we have big data caused by what? Developed by these objects. So how do we handle these? It's not easy to handle the data now. So we have we have some, we'll talk shortly. We have some technical support for the information processing. And another part is network communication, connectivity, and some developed countries that don't have issues here, but for some developing countries, we have some challenges depends on the network connectivity. I'll talk about it later. And sensing and identification, actually we use sensors and some smart devices. This one is accessible also in Africa. So, and another thing that plays a pretty good deal in the Internet of Things is these distributed techniques for each layer that I mentioned earlier. That we have some support service requests by the users, and we have a standardized some standardized protocols that have been defined to help handle some issues that we'll discuss later, and some interfaces that are managing these applications, as well as the sensors standards. And so implementing these Internet of Things, actually some smart objects have really played part. Like Arduino now, we are using these Arduino boards, Raspberries that are really helping the computation part. And the sensors that we are using, that's, you see them, multiple of them, because one system that is using Internet of Things, it may have millions of sensors. So one smart house may have millions of sensors. So what are the technical challenges behind the Internet of Things? What are the technical challenges behind the use of these sensors? Actually, I've divided these challenges in 5 groups. We have intelligent analysis, data processing, as I said earlier. We have issues with security. We have connectivity issues, especially for countries which are still lag behind the connectivity, internet connectivity. And we have compatibility issues, and also have standards. Let's see. For security, these IoT been attacked based on the layers that they play. So all the layers they're all vulnerable actually. At the perception layer, actually there's some node capture attacks that are really developing some malicious programming softwares. They really attack these sensors, and they change sometimes the functionality of sensors. Is a really big challenge. Even though they're trying to do they are trying to apply cryptography, but it is really a big challenge. It doesn't work that efficient. And we have also challenge, security challenge at network layer. That there are several attacks now on the like DOS attacks, spoofing attacks. They really attack the network layer. They disturb the data transfer, or sometimes they make the data what spoiled. So it's a really challenge also. And sometimes they change the routing protocol, the routing of the communication. And another kind of attack they receive at application layer. Also, they receive also some attacks, some viruses. We have many viruses that you see they attacking the computer and stealing the data. Sometimes they freeze the computer. And also we have challenges with the connectivity, especially for some places where internet network is not well connected. So they experience these internet connectivity issues. But for the developed country, I don't see it much because they're past this stage. But for a country like Tanzania, we're still having challenges on this. We hope that if we finish we call them Congo Taifa, the backbone, maybe things are gonna be better. We shall move to what? To the next stage. And another challenge here is the future of IoT. If we really have the future rely on the decentralization of what? Of these IoT networks. And for security experts, they're really against this because you cannot deal with this IoT, you cannot benefit from it if you don't decentralize your networks. I think for those networking especially, they understand this is the challenge that the security experts really don't entertain this Internet of Things, and they see it as a challenge. And another challenge also they see depends on the what. They are also on compatibility and longevity. As Doctor said before, that these sensors, when you have multiple sensors, actually the computation power, you have a high computation, and when you have high computation, meaning you use more energy, and sometimes they have issues on having these batteries lasting long. So we have energy issue, longevity, and also we have compatibility issues that sometimes it depends on the software compatibilities, and it can be also from the cloud services, or it can be from the devices themselves. And standards, as long as we use multiple sensors manufactured by different vendors, we have issue with the standards. I think the people in China, they're aware of this. And this also causes what? Communication protocols is a real challenge at the moment. And the other part I said that we'll talk about it is the big data. The big data itself, as I said, that these sensors, they create multiple data. We have huge data because of the nature of the IoT systems themselves, that they use multiple sensors at once. So they create multiple data, and we are having challenge on dealing with that data, analyzing the data and making sense out of it, so that you can give meaningful can deliver meaningful service to the users. So for current situation, we are having technical support. They use artificial intelligence models, but these artificial intelligence models not yet very accurate. So it's a really challenge, but they really do better. This is the future. That's why people talk about big data now, because of these sensors, data production. And the challenge also that we need this artificial intelligence, and we cannot avoid it, is inevitable. Why? Because all these systems now, they demand real-time data processing and analysis. That's why we cannot avoid artificial intelligence. We have to train the machine, and as long as machine communicate with the machine, so we rely on artificial intelligence. So this is the future, and it's a really hot research area for the young researchers and the other people who are coming into the computer science. So that's all from me. What I can conclude, I can say that it's a really big thing at the moment. And if for the people who are having interest in this research, if you can put much more attention on the further processing, data processing, we talk about the big data. It's very useful and it's very productive. For some countries, even in Asia, they have gone really far for the data utilizing the data. If Malaysia, I went once, they have this huge data center for the government that is just dealing with what? With the data. So they collect the data and they make analysis and they commercialize the data and they're selling and they manufacture really devices sometimes, depending on the analysis that they're doing. Here in Japan too, they are doing that already. And another thing, we have another area for multi-agent systems. If you can also have interest here, it's a really good research area for the newcomers. That's all. Thank you very much. Thanks for your attention.
Thank you very much, Otmar Mwambe. So I would like to welcome any question for Otmar. So we're going to take like before, we're going to take 3 questions only based on the time. So if you have a question, please unmute your microphone and fire out the question to Otmar.
Maybe I start just to open up a bit. Thanks. I think this was a very good presentation. It also nicely followed up, I think, from intelligent cars to intelligent everything. I think that was good. But I'm also again thinking the progress kind of, in my opinion, had been slow. In 2015, I was my 40th birthday. Some people gave me an Apple Watch, right? 2015.
Yes.
And I still use the same watch. It's an IoT device, right? This Apple smartwatch. So 6 years, and I looked at the latest, versions. I think they're just the same. So I'm wondering why, it's in 6 years there is no big progress, and also in general, as you said, you say maybe there is some smart homes, but okay, I'm in England, and the house we are renting is very stupid house. So really, it hasn't penetrated in our life as much as I thought it would 10 years ago. Right? It's not like we don't have smart shoes. I still don't have a smart shirt. It's just, even the smart watches are, as I told you, it's the same as 6 years ago. Why do you think it's a bit slow, the progress in general with IoT?
The main cause, I think, is security concern. Yes, security concern, especially for mobile devices. They face some challenges. Companies like Apple and Google, they face some security challenges, and it's, I think, the cause for what? For the delay. And the companies now, they are really scared. They're really scared. They're really concerned. Now they are slowing down the innovation.
Thank you.
Yeah, I was also going to say the same thing when it comes to security concern. I think that's the main blocker, because even here in Germany, for example, even though Germany has really been in the forefront when it comes to technology for many, many years, but still most of the time everything is really slow here. And the main reason is the security concern, because when it comes to security, the Germans, especially, are very, very, very strict, So just as an example, this Apple Pay that people in so many other countries had already been using to pay for services, for whatever, when you go shopping. But here, it came last year or 2 years ago. So we were like 5 years behind everybody else who already had been using this way of paying, And I was really pissed because everywhere I was going, people were already using this, and I already had my iPhone since, I don't know. I've been using iPhone since 2010, 2011, but still I couldn't use some of the services, And every time I was asking my bank, it was saying, yeah, we have to wait. There are concerns and all that, So Dr. Umut, when you talked about Apple Watch, I looked at the Apple Watch a few years ago and I was not really convinced. So I just got one end of last year, the latest one, because I didn't really see what exactly it was going to offer me back then for such a high price, you know. So
I fully agree, Kasim. Even
Do you
today,
enjoy it now?
I really like it, to be honest. But I think there is still so much it could have been able to do, but that's gonna take some time. So, for example, now you can take you can measure your oxygen level. You can take the pulse, heartbeat, and everything. But in other countries, I think you can already directly send that to your doctor. But here in Germany, I think still you cannot. And the main reason is this, something like this, you know, security concern, that you should not just send out the device, should not just be able to send out this kind of sensitive information just like that, you know?
Yes.
Yeah. And the other thing is, like, you better be careful about the the heart rate prediction or estimation from those Apple Watches. The models they are using, they're not that accurate.
Yeah, I know.
You may start panicking while things are okay.
I think the other keyword is security and privacy, data privacy. In Europe, they're very, I think that's another one is, you know, they don't want to share a lot of this private information about where you are, your heartbeat, your blood pressure. They're very, I think in Europe, they're extremely sensitive because, again, because we are in the UK, I realize with some people, for example, when you say, oh, can I get Otman's email? When I ask Kasim says, oh, first I have to ask Otman. And I say, why? You know, he needs the permission. And I go, what? I mean, so they're kind of shifting the laws and regulations. It's very difficult to share any personal information. And I think IoT is all about personal information, right? So it's quite difficult area now.
Yeah.
So, but Europe, you have done really good, you know, because you already have the complete defined framework for the sharing of information, data. Europeans, you already have it in place. And I think EU has already passed that, and you are ahead of, I think, all other countries. But the issue is now, what they need now, the experts for security, they need this that big data. The companies that are dealing with the big data do not to use the user information with their IDs. So they should make use of the data. They should utilize the data, but as anonymous what users. It's a really concern, and the government, they say no. So there is a pooling between the government and the company that are utilizing data. That's why you see that Amazons and the real first challenge is these commercial companies, because they are using clients' information for analysis, and that's why they are able to recommend some devices. So today you're gonna buy, you are buying the mobile phone, and tomorrow they will recommend a similar whatever item of a better version of that what you bought before. So they are using that. They're using your data for what? For the commercial purpose.
Yeah.
Okay, so thank you very much, Otmar Mwambe. So because of the time, we're gonna move on to the next speaker, I think, Komba JR. So he will present to us semiconductors, technologies, and application. Please welcome Mr. Komba Jr.
Thanks a lot, Doctor, for allowing me to be able to share with you about semiconductor industry. As I said earlier, that this field is so huge, it's so wide, and for the last 7 days, I've been struggling to be able to, okay, what am I going to share, and what is important and what is not important, and I thought that I can talk about the inner workings of semiconductor industry. Most of the people, when you mention what is semiconductor company, it's kind of vague. It doesn't really make sense. Is Apple a semiconductor company? Is Google a semiconductor company? what are these companies at all? So I'll walk you through what is actually happening in there. I mean, from designing all the way to assembling. And I'm going to rely on the questions because as I said, I didn't know really what to present. Just to start off, we just got to answer that question. What is it? So most of this is my opinion and what I see semiconductor industry. So it's a subsection of tech industry that deals with designing, manufacturing, but also assembling of semiconductor elements and material, silicon or germanium for the most part. And so when we talk about semiconductor, we normally talk about integrated circuits or chips, or there's a fancy name nowadays, it's called system on a chip. Essentially, you have a bunch of system in a single device. Example is, we know diode. You have P and N type. You join them together, a transistor. We have ADC and DAC. These are analog and digital converters. And then we have microprocessors. So there are essentially two designs when we talk about semiconductor product. There's ASIC and ASP. ASIC, in a sense, is application specific, integrated circuits, and the other one is standard product. ASIC is when the customer comes to you and say, okay, I need this product with this specific instructions. I want it to have these, I want the output to be 20 volts. I want it to control this and all this. And ASSP is when the business unity of the company goes out and look at the market and see the need out there. And they come and they, okay, we want to have this as one of our product. And so, as I mentioned earlier, so there essentially semiconductor companies, there are two of them. They are the ones that are mainly design memories. And we know them, the Intel, Micron, Samsung, Apple, right now, it's about 5 years ago, maybe 6 years ago, they started designing their own chips. M1 and A14, A12, all of them are from Apple. But is it a semiconductor? No. And then there's other companies that are solutions based. For example, TI, there's own semiconductor analog devices, Marvel, microchips. They're dealing with producing products, not necessarily memory-wise, but the function, how is that going to help the customer solve his or her problems? And so from that definition right there, I'm gonna just walk through the designing and how does it look like, what is it going on, what softwares are they using, manufacturing, and so on. So this designing phase, what is happening essentially is just a simulation and modeling of the specific product. And finally, they lay out the design. And then common software that is used in the industry. There's LT Spice, there's Cadence, they have essentially everything in one package. There's a Glade.
Not.
Did I hear someone?
Yeah, we'll mute him 1 second. It's fine, Keron Komba. It's just somebody's not muted. So
Okay, so that's a picture of a layout and the simulation. So on the left side, what you see, that's a layout. And this is an example for 4-bit memory module. It has, you can't see everything, but it has, there's a multiplexer in there, there's a decoder, there's 4 registers. And then on the right side is that's the schematic or essentially the layout that has been done on LT Spice. And so you start with the simulation and modeling. You picture your circuit, and you these softwares have all circuits elements that the basics ones, standard cells we call them, that you can use them to design your system. And so this is where you're starting. You're starting with the schematic from bottom all the way to the top. And then you lay out, and that's a genius actually. What I'm going to talk about, why we have billions of transistors in just a tiny small system. And so the next step right after the layout is we call semiconductor processing. So in early 60s, putting 2 transistors in one chip, it was considered a cutting edge. And then 10 years before that, and this is from Bell's Labs, they made an argument that it is impossible to have 2 transistors in one chip. The probability, actually, they said, is 50% to work. And it's just crazy. The new iPhone 12, the new chip. Now, I think Dr. Mutu mentioned about Moore's law. The idea of Moore's law is that within 26 months, you want to double the number of transistors in a chip. We destroy that. We surpass that goal. We have 14. We have about 11 billion right now. Actually, 11.8 transistors in A4 bionic chip in iPhone 12. So it is crazy. So what you see on the left side, we call it it's a clean room. When we process these semiconductor materials, silicon, we make sure that no particle can fall on them, and then I'm going to explain why. So on the right side, we see a round shape thingy. So we call it wafer. A wafer. Actually, I have an actual wafer just next to me now. If you can see right there. So this is wafer, and this one has about over 100 devices in it.
Komba, did you show us something on camera? Because right now you're sharing your screen, so I don't think we will be able to see anything. Anyway, maybe you can show us later after you finish your presentation.
All right, I'll do that. I'm sorry. And so right after the layout, what you see, the squares that you see on that wafer is the actual chip. And so the entire layout is going to put on those square thing, and we call them dies. So that's a wafer level. And it's kind of complex to explain exactly what is going on, but the layout is actually put on top of those square things. So what I said here, transistors are very, very tiny. I just want to intuitively, I want to just explain to you what is actually going on when we talk about, when we say we have billion transistor in a single chip. So 0.13 micron, it's actually a wire connecting devices. A human hair is about 100 micron. So just think about it. So this is the question I pose. Can you imagine a wire that is about 1/1,000 diameter of a human hair? So 2,400 transistors could be placed around a strand of hair. If a hair falls on a chip during a fabrication process, there is a possibility of more than 1,000 transistors can be destroyed. And so in these rooms, we call them clean rooms, that there are tons of filters, air filters, and they are changed after every 2 hours. And there's air circulation, making sure there is no a single particle. I mean, practically it's going to be a particle, but the probability of a particle to fall on a chip, it's so small. And then you can see what they're wearing right there. They're wearing these jumpsuits, making sure that they are covered and they are clean. So if you think the hospital is so clean, so this is about 100 times cleaner along those lines. So processing is a second step that we do. And actually the genius, this is, I mean, designing is great and other stuff is great, but what is people that are transforming this industry, making these chips smaller, are the people that are working in this area, developing technology that are so great and just minimize the size of transistor. I mean, from materials to connection, layout, and all of that. Come up with new rules that transform this industry. So right after that, essentially in any, not all of the semiconductor industry, this is what is happening, but a fully functioning company, it has all of these things. It has designers, they're gonna have a fab, and they're gonna have validation, verification, essentially testing these devices. So I'm just gonna give you an example, like Intel. Intel, they design their processors, but they don't necessarily fabricate. They use a contractor I mean, mostly maybe Taiwan, TSMC, they do that. And so like Apple, they don't have a fab. You see, they have a contractor that they design their chips, but someone else is processing. And then there's a reason why they're doing that. You know, I mean, am I making money here compared to the designing and other stuff that that I'm doing? So this is area where once the layout is laid out, put on a wafer, a silicon material, the device has to be tested in different environments and conditions. Essentially, what we do, we loop these parts in a range of temperatures. Now we start from cold all the way to hot. Before we actually produce, we do mass production of these devices. So engineers in this field, they write instructions. They make sure what you see on this picture down here, that's a tester. It's bigger than what you see right there. It's so huge. So what you see here is a tester head, and that's essentially it's the thing that holding this tester because of. So what you have here, you have all the you have oscilloscope, you have DC meters, you have digital meters, you have every tool that you need to use to make your measurements. And they're so precise and they're so fast. So what I mentioned here, it's what the engineers doing in this area. And this is only a test engineer. Once the fabrication is done, is going to him, and he's going to make sure that the designers, what they have done, because most designers, they don't have these tools. Designers, they have a test bench. They run their simulation there, and their tools are not as powerful as this tester and other stuff. So they have to take it to test engineer development to make sure that they can actually meet the spec of the devices. And so essentially what is happening here is writing instructions and designing hardware for that device. And I mentioned those two kinds of hardware. One of them is called probe card. It's that thing that is gonna go and touch down to these wafers one by one. It is so small. So this is a tiny wafer. We have up to 12-inch wafer. And so you can have more than 10,000 devices in a single wafer. And so that probe card is coming down and connect one after the other and make sure that there is a continuity. There is no leakage, making sure that if there's a register, if I'm writing to a register, I want to make sure I read that. So bunch of scan patterns, you can call them, or bunch of vectors are sent to these devices to create maybe a waveform or just write or read into a register or memory. And so once everything is that, once the device is tested in wafer level, we essentially package them. We put them into plastics, and that's a picture you see there. It's an actual device that is actually ready ready to go out and be connected to a system. But when we do put plastic on them, we have to verify and validate them again. What this plastic does, it alters the DC levels or DC parameters, and so the resistance is not going to be the same. If there was an offset voltage, your current is not going to be the same once you add this plastic on them. So they come back again to a test engineer to make sure that those changes did not exceed what the limit was set. So that's essentially an overview of a semiconductor industry and what is going on. And so, what are the applications of this? So, automotive, it's industry. We do make a lot of money from automotive, ton of money from automotive. Especially these autonomous cars, and we make a lot of money in airplanes. Another area that we make money is defense, space, and military. And so, if the rover, the one just went to the Mars. So the 6 image sensors are from our company. The descent and the landing, my company worked on those. We make money, some from medical. We have companies, tons of customers from there too. But a lot of money we are making from automotive. Automotive devices, because of safety reason, we make money from there a lot compared to the rest of them. And industry also, we do that. And so, this is my opinion. How is this important? How having, just asking myself, how having a semiconductor industry in Tanzania, it's for us Tanzanians is very important. I believe that we cannot get into the next level or start working right now if we do not put our money into this industry. I know there's so many priorities right now, but if we do not, because I mean, Dr. Omuti mentioned about autonomous cars, and the what is named the speaker after him, he talked about Internet of Things. We cannot accomplish that if we do not have semiconductor devices. It is arguably impossible. We need fast computers. We need fast. I mean, we need to be able to send and receive data. And nowadays, data is a big deal. But if you don't have storage, if you don't have a mechanism to transmit this data, is pointless. So our technology depends on this a lot. Not only technology, but also the Tanzanians' well-being. If we want to make a step ahead and get rid of the poverty and everything. Thank you very much. If there's any question, I'd love to take it.
Yeah, thank you very much, Komba Jr. Yeah, so we would like to welcome any question to Komba Jr. Actually, I may like to start asking Komba Jr. because semiconductors is the area of my interest as well. I mean, as you said, I mean, in automotive, we are the big consumers of these materials. One thing I think you mentioned about the testing process, I was keen to understand the testing which you are doing in your industry. Is it focusing only on the failure of the devices, or you also focusing on the prognosis? I mean, because one of the things which is challenging us in the control perspective is to understand when these devices will fail. What are the prognosis or the lifetime of these devices? I mean, the aging of the devices, for example, the IGBTs or the MOSFET, how long will it take for it to fail? Do you do this kind of testing? So that's probably question one. And the question two is mainly focusing on the limitation of the semiconductors. As we know that we are moving towards 5G and we want faster data transfer, and that's the limitation of the semiconductors one of the limitations of the semiconductors is the faster data transfer. So we need things like optical materials. Is this kind of things semiconductor industry also investigating alternative material for fast data transferring?
Yeah, so those are good questions. So testing wise, as I mentioned, it depends on so if you're putting an oil pump into a car, we want to make sure that device is going to last at least, I mean, we say lifetime, but practically that's not true. But we want to make sure it does last as long as the car is going to live. And so that's why I said the business unity, the reason why if I'm selling an oil pump to Tesla to put in their car, I'm going to charge them a ton amount of money. The reason why is because of the testing process is going to go through. That chip, that oil pump, is going to be tested in different conditions compared to an oil pump that I'm going to put in a TV. And so to answer your question about testing durability is just depending on where that device is going to go. Is it application wise? Is it a safety? Is it a medical, industrial, or just a commercial device?
Okay.
So yes, we test. We don't test it just to see how much amount of current that is drawing or sinking, but we make sure that this chip is going to function the way it's intended to function in vigorous conditions, depending on the type of a product. So yeah, the question number two is so that's where people are putting their money right now, and I'm really interested in that area at the moment. How do we incorporate the idea of machine learning with the hardware that we're using? I'm talking about chips and hardware. And so if we can make steps, come up with different cutting edge artificial intelligence. But if we do not, we don't have means to transmit or assess those data, it's a big issue. So my area that I want to just focus on is essentially in microprocessors or system on a chip, on how to help these big data people, the artificial intelligence guys, machine learning, to be able to do what they want to do, and that's a challenge. People are working so hard. And I sent a link about MIT, what they're doing right now. They are the frontier right now. They are pushing that forward, and then hopefully in the next decade, we'll be able to help our colleagues, the AI guys, to be able to do what they want to do.
Yeah, that's good. So, any other question, guys?
Maybe a common question. I think that was a very good presentation, Junior Comba. Thank you. I mean, where do you see the limit? Because as you said, so far, yes, we can track or even crash the Moore's law. But when I was doing a PhD, this is early 2000s, there were articles saying that we are reaching the limit. You know, this the wavelength, the light wavelength that we use for manufacturing of this the transistors.
Yeah.
But clearly, again, like discussed, experts were wrong, because that was 20 years ago, and we still, I think, make smaller ones. But where do you see the limit? Are we really reaching that limit in terms of the manufacturing capability of smaller transistors? Or
I mean, practically, yes. Because I mean, it depends how you do, how you define a limit. But essentially, if we could, I mean, theoretically, if we continue making this smaller, we're going to get to a point that we're going to stop. But what I see right now, not essentially making them smaller is an issue. Because I mean, if you're talking about 20 years ago, 50 years ago, is that make smaller, make it faster. That was the key. But right now, make it faster. I think it's where we are heading there, and that's why I mentioned about big data. That we are gathering ton of data. So if you can have a tiny wire, small wire can carry ton of information, vectors, we're not going to worry about how small these transistors going to be. You know what I'm saying? But that's a good question, and I'm interested. I want to see how far, how small are we going to get? And I want to mention. I'm going to mention I have a tiniest device that I just designed it. That's my last project. I want to show it to you. It's, I mean, if you think about 4x4, it's in square. It's so tiny. But there's even a tinier than that. And so we're gonna get a point that we're gonna say, no, this is, we need to find a different route. Making small is not a big deal right now. Because I mean, think about the computers that we have right now, laptops. And I mentioned about the new iPhone 12 chip. It is so small, and yet there's 12 billion transistors in it. If we can be able to transmit data in those wires, huge amount of data, I think, because if you've noticed, our phones are getting bigger now. They used to be small, they're getting bigger now. So I think we're gonna go in cycles here.
Okay, thank you. Otman, I have to leave. I think, and everyone really enjoyed it. Sorry, I got another appointment coming. But this is definitely a good discussion. Thank you very much, everyone. Thank you.
Thank you very much. Thank you very much.
Yeah, thank you.
Yeah.
Thank you. May I ask one question? Mr. Comber.
Yeah.
Yes, my question is regarding to this semiconductor. You talked about making it tiny chips. It's pretty interesting. How do you see the nanotechnology connecting with this with the semiconductor? Do you see the nanotechnology having the future of the semiconductor?
It is. I mentioned here nanotechnology. It is the future of semiconductor. I mean, the reason why we are doing what we are doing now is because of nanotechnology, nanomicrochips. They're just making things look so intriguing.
So what do you think in the future? Maybe we're not going to use even the mobile phone. We only use chip.
So when you say chips, chip is kind of general term we use.
Small, like very small.
Mwambe, I didn't hear you. Say it again.
You mean now when you focus on nanotechnology, you are reducing the size of everything. The computers were before they were such big, but now they are compacted. We have laptops and whatever. So what do you think the future is heading?
So I think we're gonna come back into where we are right now, because what I said earlier, that I don't think theoretically, I said you're gonna get to a point where you cannot make it smaller, more than that, smaller than what you have. So you're gonna try to find different ways to make your device more efficient, more, working great performance-wise, and then have all the specs that you need. Storage-wise and all of that. And so the size is not going to be an issue. The issue is going to be to access and transmit those data.
I see. Thank you.
Thank you very much, Komba Jr. So I think we have now Mr. We're going to move to the robotic automation now. So Giru, please welcome.
Okay. Sorry, I'm going to be presenting. I'm going to I'm going to try to present from my laptop, but actually speak from my iPhone because I haven't sort of my audio on the computer side. So bear with me. So name is Giru Mashibe, and today I'll be presenting you about robotics, industrial automation. Next slide, please. So the outline, I'll be able to kind of cover the background for myself, as well as where I'm at and the company I work for and what we do. And then I'll go on to robotics, just conceptually what that involves. And then I'll move on to industrial applications, specifically to the place where I'm at. I briefly will talk about limitation at the very end, and I'll be able to take questions after that. Next. So from background, originally from Mwanza, spent quite a bit of time in Dar es Salaam, and then I moved to the States for secondary school. My current residence is Georgetown, Kentucky. From educational standpoint, I have a Bachelor of Science in Electrical Engineering from Purdue School of Engineering. Next. From work standpoint, previous work in Thermostructure Incorporated. I've also worked for SIA Exhaust System. Currently, I'm working for Toyota Motor Manufacturing in Kentucky. And that's located in, as I mentioned before, Kentucky. Overall, this place was constructed in 1986. We have about 10,000 plus people. Capacity for, as far as for the plant, we produce about 550,000 vehicles a year. Full capacity. Next. So this is our lineup, the model lineup. So on the top, that's Toyota Avalon. On the right, we just started building that one last year. That's the red one, that's RAV4. On the bottom left, you see is a Camry, the new Camry. And then on the right-hand side, bottom, that's a Lexus. That was all these have been going through the major model change, going through what we call Toyota Global Structure, TNGA. Next. So overview for those who don't have understanding of automotive manufacturing. This is our plant is typically set up just like most manufacturing plant. We have what I listed here is a press, which is a stamping. That's where you get your coil, steel coil. Typically, that's where we usually start. But at the very top, you also have powertrain, which is a kind of a separate division. But from press, you go to body weld. I kind of highlighted that because that's where I actually work. That's where my shop is. That's where my department is. And from there, the product moved to paint. In this area, that's where you actually get all the paint. You get the sealer, UBC coating, and so forth. And then from paint, usually the vehicle proceed to assembly. Now, powertrain and plastic shop, usually they feed directly to assembly. and then eventually goes to a customer. So usually our customer is Toyota Motor Sales. We don't sell directly, and I'm pretty sure most automotive, I guess maybe with the exception of Tesla, usually it goes to another one of the subsidiary, and then they deal with the dealers to distribute all the products. Next slide. So my role here at Toyota, I basically work as an engineer. Specifically, my area of coverage is underbody. So what you see there is a structure of the vehicle, looking at the underbody exclusively. So the top covers most of what you see in your, where you open your engine. That's what's holding the engine. We call it the Encopa or motor compartment. And then on the bottom side is where you see your cabin side. That's where all your seat, your middle console, and then your rear seat. And then as you go further to the left, you see where your spare tire is. So all that, we call that the underbody. So any process or any equipment that touch that area in body weld, I am responsible for. Next slide. So overall, from the standpoint as far as those processes, you can see here, this is a list of particular equipment that I am that are in my area. So I support in one way or another, whether it's making sure we have the PMs that are set up correctly, make sure if we have a new equipment going forward, we actually validate it. If we have equipment that has failure, spare parts, make sure that the list is up to date. And then obviously from the standpoint as far as new equipment, be responsible to make sure that everything is meeting the standards, Toyota standard. So all in all, the key item on this, just want you guys to take from is the item related to what is ROBC, which is robot controller, stations, which is to the right of it. Some of these terms, obviously they're abbreviated. Further to the right, you have WJIG, that's your weld jig, and then you have SW ROBT, that's a power robot. So that's a number of piece of equipment in the area that I'm responsible for just my plant. So we have a total of 3 plants in one area, but in my area, this is how many equipment I have. Next. So robotics, the fun stuff. So just to get everybody in the know, a lot of people, I think they're pretty familiar on robotics. Overall, it's an interdisciplinary area where there's a multiple aspect of engineering. They kind of come together. So you have mechanical engineering from the standpoint of robotics. You have electrical engineering. In this case, for Toyota, I mean, every robot that we have has to have electrical power going to it. You have software engineering. Again, this is a critical part in it in terms of making sure we have the logic to make sure the robot function the way they're supposed to be functioning. And then you have computer engineering from the standpoint as far as just all the integrated circuits and so forth that goes into the robot controllers and station controllers that speak to the robots. So in some cases you have, for instance, I have a line that has about 40 robots. It's just one line. You have several stations in them, and those stations basically communicate to the robot, trying to provide the should I say, the priority in terms of how the work is done. And then as well as to make sure that all the particular function as they relate to the process, they work in order. So it's fully autonomous from the standpoint as far as from start to finish. When a product goes in that line, nobody touches it until it comes out. Next slide. So robotic components, typically from a Toyota side, specifically for body weld. Just one item I want to make sure I state. So body weld is the only shop, as far as I know, Toyota globally, that we're only allowed to use three types of robot. Basically, our vendor will be a Kawasaki robot, a Nachi robot, or a Yasakawa robot. Part of that is the understanding between Toyota and those vendors, just because I know that Toyota has some stake in those companies. And so for a long time, there's an agreement that we can only use those robots. So we cannot use any like KUKAs. We cannot use any of the AV robots. Other shops are allowed to be able to use them, Fanix, but we are not actually allowed to use. So anything that we do has to be one of those threes. So from the standpoint of components, typically you have a power source. In most areas, you have electricity coming in. You have air. If you have an air tool that needs to actuate, you have water for the standpoint of when you have the welding, spark resistant welding for the cooling. And then you have actuator. In this case, you have quite a bit of servo motor. Typical robot that I use have six axes. You have the base, you have the one in the middle that allow you to articulate like your elbow, and then you have another one similar to an elbow, which is joint 3, and then all the way to 6. The 6 is where you actually attach your end effector or your tool. In addition to that, you have sensors. We use sensors quite a bit because that's an indication of for the robot where it's at, what it's doing, what it needs to do. So a lot of sensors that we use are laser switches, proximity switches, limit switches, reed switches, and they allow us to be able to, in a sense, to teach the robot to do things that typically a human being can do. But because you're teaching a robot, once you program it in the same way, that's what it's going to do every time. So if you don't have some of these things, typically the robot is not going to know. So it's just going to continue functioning. In some cases, you need these because of safety requirement going forward. Next items are usually manipulators. So in this case, as I mentioned before, we have weld guns. And when I say weld guns, I mean resistant welding. But we also do MIG welding, or as we call them, arc welding. We have manipulators that are part handling, so transferring from one area to another. We use part handling as a tool, as a means to be able to do that. We do have dispensing tool. So in some processes, we do dispense material. For instance, for areas where we put two panels together where paint cannot seal, usually body weld, usually apply the sealer to make sure that there's no, for instance, there's no leaks coming into a vehicle. And sometimes we do dispense what we call adhesive material to provide rigidity to the vehicle in some areas. And then the last component is mobility. Now, majority, I want to say maybe 90% of the robots that we use are usually standalone. So you actually put the robot in one spot, and provided you did your studies from 3D modeling, you can have all your reach study confirmed. You can have all your articulation process, the path confirmed. So there's no need for the robot to move from where you actually mount and anchored. But we do have situation where it's a little bit tight space and you have to transfer part from one area to another. We have track joints where a robot will be traveling almost like a train from one location to another, carrying a part as part of the process. Next slide. So from the standpoint of controls, typically you have integrated circuit boards inside the controllers. What you can see here is a typical setup for a single robot. If you have a single robot, 1 jig, this is kind of what you will see. So you have a robot with all its 6 joints, and then you have an end effector at the end. And what you see there is listed as Kawasaki Robot Controller. That's where you have all your integrated circuit or your motherboard. You have relays in there, and then from there you have software logic. That's typically in ladder logic or sequential function that allows the programming of the robot in terms of how it needs to function. So in most cases, Toyota use, from the standpoint as far as the logic, ladder logic and sequential function. And we use from the PLC standpoint, which is what this robot, the controller, need to be connected. We use Toyopack PLC. So I know for some people are familiar with PLC. I know some other companies use Siemens. Some companies use Allen Bradley, but for Toyota, that's another requirement. For body weld, Toyo Park is the only PLC we actually allowed to use. And so for the most part, everything is standardized, everything from start to finish. When we do any automation or when we have a process coming in, the circuit, the functionality as far as the logic, the ladder logic, the safety logic associated with that particular PLC, it's pretty standard. And we work with our vendor from the standpoint as far as making sure that logic is in there, we confirm it. And sometimes when it's something that's typically a simple item as far as programming, we usually do it ourselves in-house. But most of the stuff, because of the sheer amount of equipment, where we do have a model change, usually we farm it out to a vendor and they usually do most of that. Next on this one, I want to share for this particular image is, I mentioned before, as far as sensory, we've been going forward nowadays to, which I kind of feel we're like a little bit behind from other companies, is we are using vision systems to help us really improve the means of sensing and cut the costs associated with jigs and packaging. Because packaging is a little bit more expensive when you have to have more precision as far as design and so forth. So a lot of cost is tied into that, because you have to make so many, for lack of a better word, so many packaging cassettes or pallet to be able to do the consistent pick. So we've gone to what we call vision system as a means to be able to mitigate that. And you can teach or program those vision systems that already have preloaded algorithms to be able to do the same thing in the case where you don't really don't want to worry about constraint in terms of where the part is oriented when it's coming in. Next slide. So this is one example I was talking about. So you can see here on the image, you have a robot and you have like almost like a pyramid or a cone scanning the part. This is one of the typical things that we've been doing now. We're trying to get that part from that particular packaging. So typically in the past, a team member will have like a crane or have a hoist. They'll need to go in there and be able to pick the part up. So we're trying to go away from that. And part of the reason is from the robotic standpoint, the idea is that you substitute the equipment for a human to replicate human actions. And the reason being is that you want to be able to be more consistent. Once you have a robot program, it's going to go to the same place almost consistently, unless there's some component that's failing. The other reason is safety. So in some scenario, we have a team member, like in this case, team member have to pick up the part. There's a potential for laceration hazard. There's a potential for a team member to be able to damage the part. There's also a cost. So typically at Toyota here in North America, the cost of a team member running a process is about $220,000. So when you multiply that by 5 years, you're already into $1 million. So there's a very strong push in terms of really reducing that cost and bringing it down. And then the additional part is productivity. So consider that different team member work at a different pace, and Toyota is very big in being able to rotate team members in the process. You're going to have inconsistency. So that productivity is becoming something that's impacted. As I mentioned before, we have 3 lines. We're producing about 550,000 vehicles. In the area that I'm working, my plant, we produce about 250,000 vehicles a year. Our takt time or our speed is about 55 seconds, meaning that 55 seconds, we're speeding your car outside to the customer every 55 seconds. So from that standpoint, productivity becomes critical. If you have a team member, maybe a team member gets sick, you have to get a new team member, then your productivity suffers. So quality, like I mentioned before, team member can function a little bit different. Do I hear something in the background?
We're going to try to mute that person. Tumsime, can you mute that person, please? Yeah, thank you. Yeah.
Okay. Thank you. So next slide. So as I mentioned before, Toyota Body World Robot functionality, there's 5 main, but really 3 critical ones. From body standpoint, welding is huge. Most of our robots are weld robots. Next is part handling. So transferring from one area to another. Typically, team member usually do that job, but we've gone away a little bit away from that. So you have robot that are called material handler. They'll be picking from one area, transfer to the next process. And then you have material dispensing. In this case, what I mentioned before, we have sealer robots. We have MIG weld robot. That's where materials get dispensed. So it becomes critical to make sure we dispense in the correct amount where team member is not doing. And then the last 2 have been something that we've been working with, but considering the technology, especially related to as far as detection of defect, has been lagging a little bit in our shop, or in general from Toyota standpoint. So body weld is critical for the dimension in the vehicle. From the chart I showed before, we start from the press form that panels. We basically join those panels together. And so if there's a certain section, for example, in the motor compartment where parts were not joined correctly, you're going to have an engine that's not going to be fitting. If you have a window frame on the door that's not welded correctly, then guess what? Your window is not going to be functioning correctly. So we actually invest quite a bit in making sure we have equipment that can measure consistently to be able to get dimensional quality leveled up going forward. So our target, usually we have about 2,000 points that we measure on the vehicle. And our passing rate typically is 96%. That's what we aim for. Anything below that, usually we have to kind of work hard to make sure we improve. And that we have a team that actually does the jig adjustment and so forth. And then we work from the engineering standpoint, we work to make sure all the input into a system for that dimensional measurement from the robotic side is accurate and is always updated going forward. Next. So robot setup. From our standpoint, typically what I work with is understanding the capacity. As I mentioned before, we have a limitation as far as capacity for the robot itself. So from Kawasaki standpoint, the Kawasaki provide us with a list of robots that are already preloaded into our 3D modeling. And usually they're assigned by particular weight. And the weight is critical because we have different tools that can do different things. So we have a robot that's supposed to be carrying the entire vehicle that doesn't have assembly component like tires and engine. So it needs to be able to carry quite a bit of weight. And then we have smaller robots that, because of what they need to do, they need to be small enough to be able to fit in the area. So you have that capacity requirement. Then you have a capacity requirement in terms of the process. Most of our processes, our takt time is 55 seconds. Typical weld point is about 3 seconds. So when we do a study, we need to understand all these items that are accounting for as far as the capacity of the line. You build any line or any process that's going to be running 60 seconds, Mr. Toyota is going to be coming and knocking on your door because he's going to be like, I'm losing money because you put a process that's not capable of running what's required. So those goes into our calculations when I'm setting up my process. Additional to that, layout constraint. Again, I mentioned before, you have a situation where a robot cannot reach a certain point. So to be able to understand those beforehand, you go into 3D modeling to understand where you need to be able to put the robot, how you need to be able to put a robot. And then really from the standpoint as far as the tool, understanding what the tool can do. In addition to that, because there's a safety requirement, OSHA here in the United States are pretty big in terms of understanding to keep a team member safe. Even though the robot are taught to be able to go to a certain point, human beings tend to be able to sometimes get in the areas where they're not supposed to be. So those constraints in terms of layout are supposed to be mapped as well. Most robots that we use have a virtual safety fence. And this is like, it's a software driven parameter that allow you to be able to set up the limitation to where the robot can go. So typically we usually put these in, and as part of our check on the last item for confirmation, we have a safety team that comes in and confirm all these items that they're actually in there and programmed correctly. And then there's also cost justification. So I mentioned before, is typically one process is about $220,000 per year. So if the cost of a project or cost of being able to add that particular robot into a process is greater than that, I have one time I had a project that was actually 400 grand altogether. And the requirement was the return on investment need to be 2 years. So when you take that into consideration, you need to understand, okay, how much are you going to actually save the company? Toyota does not like anything beyond 2 years of return on investment. So most projects are usually 2 years, you should get a return on investment unless it's related to a safety item where you actually, somebody maybe got hurt or somebody's going to get hurt or we're not meeting particular standard. Then that usually kind of change the game plan going forward. Next slide. So this is a typical way that you see a process set up in Toyota. This is actually, I was using what you call Carrot 3, which is a software by Delmia, to be able to map my process. So in this case, anything you see kind of like white, I think you can see doctor's cursors on there. That's a robot on there. You get that's the second one. Then you get mirror process on the other side. That's also doing the same thing. This is actually picking what you see as a key part on your motor compartment. We call these parts front side member. That basically hold your engine. What you see on there is on the yellow right there is a column. It's an actual column that actually hold the building. So when I'm setting the process, all these things I need to actually go and measure and confirm at the process. Then I map them back in my 3D modeling software to understand exactly what a limitation, when I have a robot in this particular posture or this position relative to that column, what movement would I be having without hitting that column? So all these things are looked upon to understand what limitation you have going forward. In addition to that, from the standpoint of process setup, you do have a limitation in terms of your overhead. So in this case, it doesn't show any overhead here, but in our process, in that plant, there's quite a bit of overhead because the space is so tight. We have vehicles actually being shipped above you, above the process. We need to account for those as well. So that's kind of like a little snapshot as far as automation, industrial automation with the robotic standpoint. I don't know if anybody has any questions.
Yeah, thank you very much, Giro. So any question to Giro, please? So we're going to take 3 questions. Komba, you want to speak? I think you're muted. Yeah.
Okay. So do you want to go to the software part of it, Brother Gilu, Dr. Maganga?
Okay. So you want me to go back to a particular slide?
Yeah.
Okay.
I'll tell you to stop.
I think it was
right there.
Right. Yeah.
So slide number 12, I think.
Next one.
Yeah, this one you mean.
So
Yep.
Gilu, and so I know you're using ladder logic and sequential function.
Yes.
Why chose these 2? I know there's a function blocks and there's a structured test and then in PLC. And that's the question number 1. And number 2, I don't know the control mode you guys are using. Is this state space part of it, or you guys are just using a different control mode?
Yeah. So for for the first question, why we actually use what we use, typically Toyota kind of standardize everything they do. So from the standpoint as far as software logic, all the equipment, we have what we call engineering memo. That's how we do set it up. From the standpoint of that portion of it, it's where we order from JTech, which is responsible for the Toyopack PLC. Some of the stuff is come preloaded, especially like safety PLC portions of it. There are already function blocks already in there, for which we map those. We add what we have from the standpoint of IO input-output signal coming in, and then that's what we got. We don't usually necessarily deviate from that. And part of the reason why we do that way is because from our maintenance standpoint, the troubleshooting, Toyota is very big in terms of to make sure everything is simple. That way, whether it's a team member coming to maintain the equipment from one area to the next, it's always the same. It doesn't deviate from a person to a person. Now, in the past, why that was chosen from that standpoint, I cannot begin to tell you. Now, the next question, I didn't catch the next question. Can you please repeat the second question?
So in terms of control, I mean, I wanted to know if state space model is what you guys are using to design your controllers, or is there a different controller you guys are using?
Yeah, we don't necessarily use state space controller from that standpoint. I do know from looking at Toyopack, their PLC. I mean, we if I was to compare to what I've seen from other automotive, I think we're a little bit step behind. And part of that is Toyota is very conservative in terms of that. So if you look at previous generation, we are more in line with the previous generation than we are compared to today. I think Alan Bradley PLCs and Siemens are a little bit more advanced from that standpoint. I mean, we have like some of the relays that you see, they're not like, I would say, state of the art going forward, if that can help answer your question.
Oh, yeah, it does. Because the reason why I asked that, because right now in school, what they do is actually AB PLC. It's a big deal. And essentially, that's the type of hardware. I mean, PLC they're using there, and like an industrial standard at the moment.
Yeah. So, and for the most part, I think that's regulated. I think I can remember what organization that regulate all that. But I know there's been a strong push trying to get there. But our plant, like I said, we're using some equipment that are originally to the plant, and the plant was built in 1986. That kind of give you an idea what it was, the technology back then. So
are you saying that MATLAB, you guys don't use MATLAB at all? Or
no, we don't use MATLAB at all. No. No.
Yeah, I think for the robotic control, because most of the operation you're doing, they are just sequential. So probably the PLC, the ladder diagram maybe could be sufficient enough, because you have specific kind of maneuver you want to do, isn't it? So it's a bit different sort of control as compared to the other type of control you normally deal with.
Yeah, but I know one thing, Doctor, that there being a strong push going forward with, I think the previous speaker, Internet of Things.
Yeah.
That's one thing, there being a strong push. And with that, I think the information want to become readily available. So going forward, there's been some concerted effort to see how we can address that. But that's also going to involve making sure we upgrade some of our control unit, because the simple things as, for instance, all the issue that the robot may have, for instance, he didn't get maybe a same proximity switch did not get read. We don't know, I mean, we do know because the team member goes in there and checks it. But from Internet of Things standpoint, the thought process is to be able to get that information readily available to know exactly what it was and when it happened, what time it happened, kind of thing. So.
Thank you.
Yep. So Dr. Altman, please go, if you can go to the last slide. I'd like to ask a question.
Okay.
Gilo, thanks for your presentation. I'm just a bit curious about the processes you take to create your design. So for this particular environment, what tools would you say what tools are you using to create this virtual environment? And is it a dynamic one? And also, yeah. So there's a second part of the question. So when you test your software, are you able to test your software with this virtual environment that you've created?
Yeah, so interesting. So from the standpoint of like as far as software, let me just, I guess, maybe answer the first question first. The tool that we use, we call Delmia has a 3D modeling software, which is called KR3. And in there, Toyota has worked with Kawasaki and Nachi and Yasukawa to be able to get all the information and the functionality of the robot into the system. So the actual model of the robot is already in there. And what that does is it allows you to know what the limitation of that particular piece of equipment, when you actually put it in the same location, what it can do, and what are the things that you cannot do with it. And then from there, we had to design our own tooling to some extent. Now for spot welding, usually Toyota has a list of what you call the gun arms, which is provided by another vendor, which is Obara. It's already uploaded into a system. So you put them in there and you know what they look like, and based on the actual drawing that have been provided. And so you can actuate them with all the kinematics in it and be able to know that you can reach at this point, you can reach this point, you can reach this point, you cannot reach this point. And then so from there, you are able to design your process and say, well, you know what? Because of what this particular tool can do, I can only do this, this, and this. Now for part transfer, we work with the vendor to make sure we design a tool that can actually meet the requirement in there. So when the design is finished and we upload it to a system, it's already clear for the standpoint as far as what is the function of the tool. Now, if the tool is not meeting the standard, because we have a standard sheet to what we actually check each item in there. For example, the required IO, required data, what they call keygen, and required input outputs, and also the required weight associated with the robot. So if you have a robot that's like a 100 kilogram capacity, the tool has to be under that, because you have to account for the tool and for the part that's carrying it. So all that you put in it, and when you do a study, you're already accounting for all those things. And then, sorry, for the second question, can you repeat your second question?
Yeah, so the second question is about the software you designed for the robot itself. Are you able to test it within this environment the virtual environment that you've created?
The only part you are able to test it out is basically just to see if, for instance, like proximity switch, is it actually at the position where it should be able to sense? Because each proximity switch or read switch has a range that's supposed to be able to actually trigger. But for physically doing it, you have to actually be able to actually be in a real environment. So you cannot test some of the aspect of what's needed in this environment. This only gets you close halfway there, but physically getting everything else is what you actually need to be able to actually testing out. The actual logic itself, as far as how the issue function, you don't. Now, there's a certain part of it you can do. For example, like all the robot programs, you can actually do them in this environment. And then once you do them, you can dump them in the actual robot and test them out. Does that answer your question?
Yeah, it does. Yeah, thanks.
I guess,
No
Licky, Dr. Licky, I guess you were interested to see that if this tool, for the 3D modeling is capable of simulating this stuff as well, like these robots which have been placed in here, are you able to simulate to see that the kind of the maneuver is going to do to the yellow block set there, you have sufficient distance or is it just for visualization?
No, not the visualization. I think he's answered that. I mean,
Yeah.
the physics aspect and the dynamic aspect of the environment is there.
Yeah.
And then you can reach different aspects of the environment itself, which is what I wanted to know. And yeah, so I think it's a good tool in terms of visualization and testing. Yeah, so I think the question is answered.
Yeah, definitely. The tool actually saved a whole lot of time from the standpoint as far as from start to finish. Because if it was a situation where we were just gonna trial and error, that would create a lot of cost up, because you'd be setting up and reset kind of thing. So this is just basically allow you to be able to start and know it's good before you proceed to the next step. So.
Okay, so thank you very much. So I think because of the time, so we'll move to the next presenter, and then I think it's me, if I'm not mistaken.
Thank you, Doctor.
Yeah, thank you very much, Kiro. I think it was quite interesting. So I'll share my screen. You should be able to see the presentation. Anyone can confirm that?
Yeah, we can see it.
Yeah.
Okay, yeah, so actually it's quite interesting because what I'm presenting, it may sound outdated based on where we are moving in terms of technology, because as you may know that we are moving toward electrification, towards artificial intelligence, machine learning, self-driving cars. But this piece of work which I did it's an old piece of work where I was looking on how we could recover waste heat from the engine exhaust. So that's the idea, how you could cover the waste heat from the engine exhaust. And we know that the engines are there to stay maybe for another 20 to 30 years before everything can become electrified. Of course, this is quite ambitious, but let's see how we could recover waste heat from the engine exhaust. As for those who are familiar with the engines, we know that the engines are still inefficient. So you have only 25% of the energy, or the energy from the fuel, which can be used direct to the engine, but you have a lot of losses. Majority of big losses is happening to the engine exhaust in terms of heat, and you got another 30%, you lose it in terms of for cooling, and then you have like 5% also you lose in terms of the friction. So how can we improve the efficiency of the engine? So that's the idea of this presentation. So in terms of the content, so I'll give you the background. I think my slide have moved a bit. So this is supposed to be the first slide, but ideally I will cover the introduction background, which I've already given. And then I will speak about a particular device which called thermoelectric generator technology. So this is the technology which is used for recovering this waste heat from the engine exhaust. And then I will show you how you could integrate this system and how you could do the hardware testing. And then I will followed by the power condition unit, which basically is the device for trying to match the load resistance and the internal resistance of the thermoelectric. We'll see in detail. And then I will speak on how we could also further maximize the efficiency of this thermoelectric generator, because they are still inefficient themselves in terms of the material. So we use this called maximum power point tracking algorithm. And then I'll talk about two algorithms. One is called extreme seeking controller. And also I'll talk about my particular controller, which was the extension of the extreme seeking. So it's called state dependent parameter extreme seeking. I will finish with the simulation and experimental results. Okay. So based on what I presented about the inefficient issues of the engine, so in order to improve this efficiency of the engine, so you could use this so-called thermoelectric generator. So the thermoelectric generator, you can implement within the engine exhaust just after the catalytic converter, and then you'll be able to convert heat into electricity. So the main advantage of this is because that you already lose this energy anyway, so the energy you recover from it is free, it's a free energy. And also this thermoelectric material, they are not moving. So they are solid state system. I think Comba Gerard was covered things about the semiconductors. So this thermoelectric material, basically, they are based on semiconductors material, which is P and N type material. So we'll see in detail. The major limitation of this thermoelectric material is that the material themselves, which are available commercially, they are still inefficient. Yeah, and this is because of the heat to electricity conversion. So one of the common material used is called bit-telluride material. So they are still inefficient. So you could further improve the efficiency of the thermoelectric generator itself by implementing maximum power point tracking algorithm within the power conditioning unit. Yeah. So in terms of the thermoelectric generator technology itself, so the thermoelectric generator is made of the P-type and N-type material. So these are the semiconductors material. So if two dissimilar junction, if you put the top side, let's say at the hot temperature, and then you put the bottom side at the low temperature. So what you're trying to do is to establish the temperature difference. Then you can use this so-called Seebeck effect. So the Seebeck effect, what it does is it does convert heat into electricity. So you could basically get this electricity from putting this material in the temperature difference. So where is the application of the thermoelectric generator material? So they are used in larger industrial finances. And of course, we have seen BMW, they have used it from their 530i. So they could also, I mean, they could recover waste heat from up to 1 kilowatts. Of course, for the typical automotive application is mainly like 500 watts. So it's like 0.5 kilowatts. So that 0.5 kilowatt in terms of power, you could use to power the DC-DC loads. Yeah. And in Japan, they use it for industrial finances, as mentioned. So you could recover up to 1 kilowatt. And also there are some low kind of the material you could use in the watches as well. So these are the kind of the people who have already invested on this technology. So you got the BMW, you got Ford and GM. So you see that this is the thermoelectric generator itself, just after the catalytic converter. So how do you integrate the thermoelectric generator within the powertrain? I mean, you have seen Giru has presented the robotics, and I mean, in terms of how the process is. So this one will sit within the powertrain. So you have the engine, and then you have the catalytic converter. So from the engine exhaust, you have your hot side end. So the hot side of the engine, you are talking about 600 degrees C. So you cannot really apply the 600 degrees C to the thermoelectric generator because the fact that the material cannot withstand such high temperature. So what you need to do, you need to have heat exchanger, and that heat exchanger will drop down the temperature to 250, for example, in the hot side end, and the coolant on the exhaust, I mean, so the coolant from the radiator could use to cool the cold side. So what happened, the input to the thermoelectrics will be the hot side temperature of the water, of the gas from the exhaust, and the hot side will be, the output will be the voltage and current. Because this voltage and current is depending on the temperature difference of the hot and cold side, then you need to make sure that you maximize the output power generated. So in order to maximize the output power generated by the thermoelectric generator, you need a maximum power point tracker. So maximum power point tracking is, I'll explain in detail, but is applied in different domains. So you could see in the PV, you could see in the fuel cell, etc. So once you have maximized what generated from the thermoelectric generator, then you could dump that energy into the battery. So this probably is almost similar to what I just showed you. So you got the hot side of the thermoelectric module. So what happened is P and N type, they form thermoelectric module. And if you configure thermoelectric module as in series and parallel, they form thermoelectric generator. So the thermoelectric generator will combine several modules of the thermoelectric. So you see, you have hot side and you have the cold side, and then this come out is the power, power generated. You condition it using MPPT, maximum power point tracking algorithm, and then you send to the DC-DC load. So this is part of how I'll show you how I sandwich it, the thermoelectric generator. So we got the coolant from the chiller. So we had the water from the chiller, and you have the heater block here. So you power the heater block. This was just for testing when we are doing the characterization of the thermoelectric module as well as the working out the maximum power point tracking algorithm. So the heater block will give you the hot side temperature, and the coolant from the chiller will give you the cold side temperature. So you see the thermoelectric module is sandwiched in between here. So by keeping it, as is mentioned before, in the temperature difference, then you'll be able to generate that electricity. So this is the total configuration. So what we have seen here is just a single module. So in here, I have, it's a bit difficult to see, but what I have here, I have the heater. So this is kind of the where I can compress, I sandwich multiple modules. So I have multiple modules sandwiched in between, and then I have a coolant loop. And then of course the controller is sitting in the Simulink and MATLAB. And then you have a DSpace for visualization. So for data acquisition, and of course for the hardware in the loop testing. So the hardware in the loop testing is done with the DSpace interface. So you have the DS1104 because it's give much bigger switching frequency. And you got the load, this is a battery, it's a 12-volt battery. And then of course you got some other power supply unit to power the other component in here. So this is the overall configuration. And now, so if you see here, this is kind of giving you how do you come from thermoelectric module all the way to the load. So thermoelectric module, as I said, is one. When you have many, they form thermoelectric generator. So the thermoelectric module output voltage is the temperature dependency, and you cannot really, if you want to maximize what is generated out of here, so you need to use maximum power point tracker. And the maximum point tracker, so you get the voltage and current as an input to the MPPT, and then you work out power, and the power you find out an appropriate duty cycle, which will drive the PWM signal in order to drive the synchronous DC-DC back boost converter. So the power conditioning unit is this piece in highlighted here. So what is maximum power point tracking algorithm? So maximum power point tracking algorithm is an iterative approach, which basically you're trying to do the perturbation on either your duty cycle in order to reach to the maximum power point. So the idea is you are trying to match the internal resistance of your supply or your source of energy or your source of power, which is the TG or electric generator for this case, with the internal resistance, so with the load resistance of the DC-DC converter. So basically you are altering the operating point such a way that the internal resistance of the supply and the load, they are matching. So that's where you get the maximum power point tracker. So there are multiple algorithms which are used for that. One of the common one is called perturbation and observe. Yeah, so you perturb and observe. So by matching the internal resistance of the supplier and the DC-DC, you could have an extra power or an extra wattage power, yeah, because you are shifting the operating point. If you were not to use MPPT, you will be operating at this point here. So you lose this amount of power. So the algorithms for maximum power point tracking, which I'm presenting today, is so-called EAC. EAC is Extremum Seeking Controller, and SDP. So SDP is the one which I end up doing the patent. So I got the patent for SDP EAC. So extreme seeking controller, so next slide. So this is an adaptive algorithm, which is a model free, because most of the adaptive algorithm, they tend to need a model. So you tend to need a cost function in order to minimize the cost. So extreme seeking controller, what it does is it seeks for maxima or minima of a function. Yeah, and is working in a closed loop, what you call it, closed loop operation. So imagine this is your plant. Yeah, so this is your plant. So the plant will have dynamics. So what you need to do is to deassociate the dynamic of the plant with the steady state, or we call it static nonlinearity. So by doing so, basically you make so this is the part of the extreme seeking controller, the bottom side. You make it so slow, such a way that the plant, you eliminate the dynamic, appear as a static nonlinear. So as long as your input and output have a maximum, so if you assume it's a convex function, so the output of it, you pass through high pass filter to remove the high frequencies, and you demodulate it with the sinusoidal. So this is a perturbation signal. So you can either perturb it with a cosine, or you can also perturb it with a square wave. But one of the commonly used is the sine wave perturbation. So the sine wave perturbation, and then you pass through an integrator. So the integrator is there for finding you the gradient. So what you know that the adaptation will be done with the integrator. So you know that if you have, let's say, a parabolic or a convex function, if you find the derivative equals to 0, that's where your maximum lies, isn't it? So what happens once you have found that, then you need to do modulation. So we are doing demodulation with the sine wave after we have removed high frequencies, and we are doing modulation to give that perturbation. So what will happen is this feedback controller here will keep doing perturbation until you reach to the maxima. And because you are perturbing with a sine wave, then it will oscillate around the maximum operating point. So this is suitable. It converges faster depending on how you select your the filters, cutoff frequency for the high pass filter, as well as the gain of the integrator. So, however, this type of approach is suitable when you have a local maxima. For example, in solar panel, when we have multiple maxima, especially when the solar panel is shaded, this algorithm will not be able to work appropriately because it will converge to the local maxima. But for the TG application, it's absolutely fine because we normally have a global maxima, so it will converge to the right maximum. So the only limitation of this controller here is the fact that because you have perturbed with a sine wave, when it converges to the steady state, once it has searched for the maxima, it will oscillate. So it introduces so-called limit cycles. So the limit cycle, they could associate with the degradation of the component. So they are not desired limit cycle. So what I want to do is to introduce a function, which is called a state-dependent function, which basically will reduce the magnitude of the perturbation signal exponentially based on the variance of the output of the integrator. So by doing so, it means once I've found the maxima, this decaying function will be able to converge and remove those limit cycle. But I need to converge to a so small so that wherever the maxima changes, I can always find it. Yeah, so in order to find it. So one of the guy, I don't know if he's in the meeting, he say that I went for something called simple, robust, and easy to debug. Because most of the controller, when you develop in academia, they tend to be complex, but when you put to the actual hardware, to the actual system, you won't be able to, they won't work properly. So because this was the industrial solution I was providing to the European thermodynamics, it has to be simple, robust, and easy to debug. So these are some of the simulation study I did. So usually when you do for this type of activity, you start everything in MATLAB Simulink, do simulation, do comparison. So at the time I was using this Perturb and Observe as a benchmark because it's a well-established, simple controller. But the disadvantage is if you have something which change faster, you won't be able to do that. So this is kind of try to see the black line here you see is where you have your theoretical power, and the red one is extreme seeking controller. So you can see that the extreme seeking controller, it converged to the true maxima much faster, and it give kind of what you call it, consistent in performance, regardless of the variance of the power. So this was the simulation, and then I went up to do what we call it emulation of the thermoelectric generator. So you can emulate the thermoelectric generator by applying power supply units. So you don't need the actual thermoelectric module. So you emulate it with the power supply unit connecting with the rod resistance. And this was just trying to see the performance, transient performance of the thermoelectric, what you call it, the transient performance of the extreme seeking controller. So I changed the operating point for different operating points and see that the controller converge. But you can see that once it reached to the steady state, it oscillates because of that perturbation I was mentioning about of the sine wave. Yeah, so this was just a standard EAC. And now I run kind of switching in between. So I run the existing, so it's extreme seeking controller, but some people, they call it perturbation-based extreme seeking controller. And then I ran my controller, which is a state-dependent parameter extreme seeking controller. So I switch in between around 200 seconds. So this was again through the emulation of the thermoelectric. So you can see that the perturbation-based, it enter. So this is the true power. It entered like a limit cycle. So you have oscillations here. These are limit cycles. They are not desired. But when I switch around 200 seconds with my controller, you can see that the limit cycles have decayed. I mean, you don't have those massive oscillations. Yeah. And again, so this is also another comparison on, because here I was just doing power, and here I just run the comparison of the extreme seeking with the SDP-AC. So you can see the duty cycle, current maximum power point, voltage maximum power point. So you see my controller, which is a state-dependent parameter, will set exactly the same perturbation at the extreme seeking, the same as the extreme seeking controller, but over time, the black line, it will converge to the theoretical. Yeah, so it will not have ripple because I minimize the ripples or the limit cycle. So these ripples I'm minimizing, I can't decay them to zero because I need to be able to detect when the set point have changed. Again, so this was part of the transients analysis, but this time I use the actual thermoelectric generator in the actual setup. So it's not emulated this one, but in here I just did extreme seeking controller. So the red one is the theoretical, but you can see the controller, it oscillating around the theoretical. So you are tracking around the theoretical, and you see the temperature, delta temperature difference. I started from 200 all the way down to 70-ish. But the controller, because this was just simple extreme seeking controller, you are able to sit around the target. So in conclusion, what I can conclude is like we have seen that we could recover waste heat from the engine exhaust in order to improve the efficiency of the engine using thermoelectric generators. So this is one of the applications. There are several applications of the TEG. I was mainly focusing on automotive application. I think I've demonstrated it to you that the simulation and experimental results, and also the SDP EAC, state-dependent parameter, is tracked within 4% accuracy. Yeah. So that's it from my side. And unless if anybody has got some questions, I'm happy to take them.
Hi, Usman.
Hi, Tohid. Yeah.
It's nice to catch up after some time.
Yeah, it is really nice. Yeah.
Yeah. Excellent piece of work, as you have done previously. I think I'm aware of that.
Yeah.
So I can see you used MPPT algorithm to achieve max available power.
Yeah.
Right. As I know that you have done this work a few years back, and then you have moved to industry, and probably you may not be in touch with that sort of work anymore.
Yes.
My question is, if you have a chance again in today's world, today's date,
yeah,
would you do it differently? I mean, is there any better option available than MPPT, or you think you are not up to date on that?
That's a good question. Let me check if somebody is on the call. Let's see. Simon, are you here?
Struggling with the mute button, as I always do.
Okay, so Simon, I work with Simon, and one of the work we are doing at the moment, we are working on the fuel cell. So I think you might have known the JLR is in the venture of making a hydrogen car, and Simon is the work stream lead. And I remember he was asking me about the MPPTs and the applicability of the MPPTs. So he has done some work of it. So yeah, he's doing some work on MPPTs, maybe not necessarily what I came up with, the state-dependent parameter. But again, the applicability of the maximum power point tracker is still visible. Yeah, so maybe I wouldn't have done any different. It's just maybe I need to find somewhere to apply what I've done to other kind of projects, not necessary for the engine exhaust, to maximize what we call the waste, to maximize the output generated from the thermoelectric generator for waste heat energy recovery from the engine exhaust. Probably it's better to look for the different application, as we may know that the engines, maybe they don't have longer lifetime, isn't it? So we are talking in next 30 years. I mean, I don't know, Simon, unless if you have something to add up on that.
No, I mean, that's part of the research project. So the hydrogen fuel cell vehicle that we're demonstrating at the moment in JLR is just for us to assess the technology and whether it would make a viable product. If it does, then obviously JLR might get into the business of building its own fuel cell. And if we do that, there would definitely be a need for a controller like this, because that's an essential function of a fuel cell, is to do that maximum power point tracking.
Yeah.
Yeah.
Okay. Any other question?
Doctor, can you go back to the functional the blocks, functional blocks? I think one of the slides. Yeah, there, yeah, right there. So you know, I've never seen an integral controller by itself, and whenever I use integral controller, it is when I want to remove the steady state error caused by proportional. Do you want to explain a little bit here about why did you use this integral by itself?
Yeah, so that's a good one. So I will have to use my snip, and my snip is the famous. I think someone know me for like snipping things up. So imagine, because like I said, extremum seeking controller, it seek for maxima or minima of a function, but it doesn't have a prior knowledge. So what it has in terms of the knowledge is just the input and output. As long as they have a minima and maxima, it will try to search it. So imagine you have a function which is like this. So you normally have convex and concave. So imagine you have a function which is have a maxima like this. So we know that if you want to know that you are at the maxima, you differentiate, isn't it? So if the derivative of a function, any function, I say dp dt, rate of change of power with the rate of change of the duty cycle, if this is equal to 0, you know that you are at the maximum, isn't it?
Right.
So that's the idea. So the thing is, you have the gradient searcher. So in here, I simplified this by putting a high pass filter. Usually you normally have a low pass filter cascaded here. So the low pass filter, and the high pass filter, these two, they allow you to search for the gradient. So we normally call it gradient searcher. Yeah, so they search for the gradient. And then when you search the gradient, you need to keep modulating that duty cycle. So basically, imagine this is power, and this is the duty cycle. So the duty cycle, let's say, start from 0% all the way to 100%. Yeah. So you will search for power, and you do the modulation. Yeah. So you find the initial duty cycle. You keep perturbing. So basically, you are removing the DC component by filtering with the high pass frequency, and you use low pass filter here. So you do the gradient search, and this one is there to do adaptation. So this is an adapter, if you could say so. It's an adaptation. So it will keep moving this. You keep moving this duty cycle, and of course you will keep modulating until you will pass your maximum. So if I use the black notation here, the black pen, so you will keep incrementing. So I assume that we're in this direction until you pass. Because you have an adaptation capability using an integrator with some gain coupled into that, it will say like, look, you have already passed your maxima, you need to go back. So it will go back. So in the end, you start to oscillate around the maxima. So you are not converging to the maxima. So this is like, because I've drawn power versus duty cycle, if we were to draw in the time series, the response of time, so basically you will have your power versus time will do like this. So you reach to the power, you drop, you reach to the power, you drop, you reach to the power, you drop. So now imagine that you have increased, let's say the engine exhaust temperature increased, and now you are outputting more power. Yeah. So let's say this power has shifted to another point. So that's where your integrator come into play. So it will be able to, because you need to keep some perturbation, it will be able to say that, okay, now things have changed. So you need to find where your maxima sits. But again, this plant is not just a plant which have got this kind of, you can see this is a quadratic function here. It's not just having this quadratic. Your controller, which is the feedback controller here, it should be, I mean, the dynamic of it should be slower in order to allow that you can see this map as a static nonlinearity. So you are removing the dynamic of this actual plant. Sorry, I have to explain in detail, but.
Thank you.
Yeah, that's how it is. Any other question? Otherwise, we move to the next speaker. And I presume the next speaker is one of my good friends. I've known him for years, Dr. Adama Fofana. And also he will present some of his work on key optimization.
Hey, Doctor.
Hello?
Yeah, Doctor, I had one more question about
okay.
your path. So in the past, I know some have used pulse width modulation to be able to kind of attain some level of, should I say, like maybe regulate the power. Is there a particular reason why? Did you look into that from that standpoint for what you wanted to do, or was that going to be something that's going to get you to the opposite end of what you wanted to achieve?
Okay, so it's a good question. I will go back to which slide is a good one. Yeah, probably this slide here. So maybe not this one. Yeah, this one here. So this MPPT controller itself is, if I snip this one. Sorry, I'm coming from academic background, so I tend to show things by, it looks like I'm teaching, but
No problem. That's fine.
Yeah, so it's just the typical me. Yeah, used to that. So what happened is you got the voltage and you got the, yeah, someone is not muted. Oh, that's good. So you got the voltage and current. So this one technically give you power. So the power you get, so you need to work out with the MPPT controller, you need to work out the duty cycle. So the duty cycle need to go, because this is a simplifying of the drawing, need to go to the PWM. So I'm coming to the point which you just raised. So this PWM signal basically will be having a varying duty cycle. So that we allow the duty cycle to vary to drive the pulses. So here we'll have the pulses of the different duty cycle, which will drive the converter. So the one you are talking about, the PWM signal, what they do is you could eliminate the MPPT. So when you eliminate the MPPT, so basically what you do is you don't need to sense what the thermoelectric does. You fix the duty cycle, let's say to 50%. Yeah, so that's what they use the PWM for. So you fix your duty cycle to 50% or 40%, and then you generate the pulses, and the pulses will drive your what do you call it, your back boost. The problem with this, you are not really tracking the MPPT. So it's the same of having something like this. So that duty cycle you have selected, it could be optimal. So imagine that your power was changing like this, like this. So that duty cycle will be like this, based on how you selected. So it will say, okay, I don't know this power, but it may be optimal around this area and find the correct, so you get the matching. But when you come here, because it's fixed, it may not be able to find. Whereas if you allow your MPPT algorithm to track it for you, and of course it need to be cascaded with the PWM signal, you'll be able to say, okay, I need to find the appropriate optimal duty cycle, and then find optimal duty cycle. Of course, it's going to be faster, just start drawing there. And another optimal duty cycle. So you can see the difference between these two controllers is the fact that I'm able to track maximum power point tracking, while the fixed one, it will be optimal for a particular duty cycle, a fixed operating point. So, but both algorithms, they need to have a PWM signal. If I answer your question, Guido?
Yes, doctor. Thank you.
Okay, cheers. Yeah. So, Adama, unless, yeah. So if you have any other question, I think we can continue offline. Anybody else? But because of the time, so I would like to welcome Adama Fofana, please. Yeah.
Thank you very much, Dr. Osman. Yeah, my name is Adama Fofana. So let me probably share my screen. Can you all see my screen?
Yeah.
Yes.
Yeah, thank you very much for this presentation. So like Hotman said, I think we know each other for so many years now. We've studied together at Coventry University, and we both graduated at the same time. Still remember, long time ago, about 5 years now, roughly. Yeah, so today I'm going to present a gear shift map optimization using a genetic algorithm. So that was one of my one part of my study when I was doing my PhD. So this is based on dual clutch transmission. So I don't know if you are familiar with the automotive transmission. So the dual clutch transmission I was working on was having a 7 different gear ratio, and then having 7 different gear ratio, basically that will impact on the fuel consumption. The way you drive your vehicle will impact the fuel consumption, selecting based on which gear you are. And so one of my study was to look at developing an algorithm which can be used to optimize the gear shift point. And based on that, we can try to see how we can reduce fuel consumption, which will impact on the CO2 emission. So that was my main study. So before we start, so this is the content. I will first explain the problem formulation, because I think one of the people need to understand when you doing optimization, the first thing people will think is taking an algorithm. Basically, algorithm is not the solution. I think the most difficult part first, when you start, is to formulate properly your problem. The problem formulation, I will say, will represent almost 80% of your work, because if you don't define properly your problem, you will not be able to optimize and get a good solution. I think that's the first thing we need to understand when you're doing optimization. Optimization algorithm should be the last thing you need to think about it. First thing is to really properly formulate your problem. Then after that, now you can select an optimizer. So I will explain this, and then I will take an example of gear shift map optimization, how we can formulate the problem of gear shift map optimization, and then using an algorithm, which will be genetic algorithm. I will explain how we basically select genetic algorithm to be able to minimize fuel consumption. And after that, I'll give a conclusion. So to first start, like I was trying to express, is the problem formulation. The problem formulation is the key. First thing, we have 4 main steps to define your problem. First of all is to define the design variable. So the design variable are basically the parameter you will modify to be able to see any improvement in your system. So this is called the design variable. Then after that is you need to find an objective function. So an objective function is, for example, in this case, our case would be the fuel consumption or CO2 emission. Basically trying to find a function, a cost function, which you can utilize when you change your design variable, will have an impact on your cost function. Basically here, reducing fuel consumption. So that's the main thing. Then we always have a constraint. So constraint would be, you cannot necessarily say you will only reduce fuel consumption, because you need to understand when you say you will try to reduce fuel consumption, it will impact on other things. So it can be, for example, the vehicle durability. Vehicle durability can get worse when you're trying to change your shift map and trying to see if you can reduce fuel consumption. You cannot only do that, you also need to think about other things, because it's all about sacrificing. If you sacrifice something, then it will have impact on other things. So you have some kind of boundary, you need to think about it. So this is basically the constraint. Then the last one is basically in your variable, you cannot change your variable, you have some limitation. So what we do, we'll set up some kind of boundary on the variable. So this is the last step we will do. Then once we have done that, now we can move to selecting an algorithm. You have tons of algorithms, tons of algorithms. I mean, they all have the advantage and disadvantage. I will explain that later on. So, but what you need to understand in terms of algorithm, you have 2 main different types of algorithm, which is deterministic and stochastic. So I will come to that later on as well. And then once we have select now the algorithm, now you can move into implementing your problem formulation and around that specific algorithm. So problem formulation, first of all, you can have design variable can vary from 1 to n. So it can be 1,000, but you need to be very careful. You need to try to limit your design variable, because this can have a computational impact on your algorithm. So if you can try to minimize the number of design variable, it can be good. I will show you later on the design variable in the gear shift map optimization. You will understand a bit better. Then we have now here the cost function, the objective function, which is, for example, reducing fuel consumption or CO2 emission. Even we can even consider drivability as well. Then inequality and equality here is basically you trying to formulate mathematically a constraint, basically to constrain your cost function. So again, different example will come later on. I will try to explain. And then the last thing is within your design variable, you can set some kind of boundary which can be defined between two different variables here, which is in this case A and B. So this is like a mathematical template when you formulate your optimization problem before you can start doing any optimization. So you have tons of literature which explain that, but the main thing here is when you do optimization, these are the main stepped objectives you need to look at before you can move into selecting a typical algorithm. So the next thing now, so if I try to take an example of how do we formulate, for example, and select an objective function, because when you do optimization, you have different type of doing optimization. You can either select a single objective function. Let's say you can just say, I will consider fuel consumption, or if you have more objective function, because sometimes you can have more than one, which even 3, 4, 5 different type of objective function. So this become a bit more complicated, and you have different ways of trying to combine into one single algorithm. For example, here, in my case, I was having 5 different type of objective function, but just as an example, if we try to limit it to 2 different objective functions, so the way you do it, you will allocate some weighting formula into such that you can basically reduce your objective function into one single objective function. So that's basically one of the methods I've used a lot during my study to reduce my objective function into one single objective function. It's just based on a mathematical formula, which is just you trying to weight. You basically create 2 different weights, and the sum of the weight should be equal to 1. If, let's say, I'm having 2 different objective functions, the way you make sure that you can convert it into one. So this weight, W1 and W2 here, for example, can be 0.5 each, which will give you the sum of 1. So by doing that, you will reduce your objective function into one single objective. And then the other one is what we use as well, is basically called the Pareto optimal solution. So when you have 2 competing objective functions, so you will basically plot them into 2 different dimensions. And then, so when you plot, so these are, if you imagine these are different solutions you will obtain. And each of the solution will have the value of objective function 2 and objective function 1. So you plot them. The best one here, when you plot them in 2D, so the best one are basically the red one, which is called the non-dominating part of your solution. So this is how you can obtain a nice shape form of solution. So in this case, so the best solution would be something around these 2 here, which is just you trying to find something which would be closer to the origin between both. This is how we select the best solution. When you plot them, you're trying to plot and compete each objective function against each other. So this is how you basically define which one is the best solution. So you need to find a compromise. In this case, you cannot say this is the best or this is the best, because as you can see here, when this is increasing, So this is basically decreasing. So in this case here, it is good in terms of function 2, but bad in terms of function F1 here. So you will come to select something which is in between, probably this one or this one, based on how you, based on what are you constrained. This is how you select a good solution. Yeah. And then, like I was trying to say, so we have two different types of optimization algorithm. One is the deterministic, and the other one is stochastic. So deterministic algorithm is something, if you imagine, you can formulate a mathematical optimization where you can predict what could be the output. So you can in advance, you will know what's the output. But in terms of stochastic algorithm, this is something based on random selection. So you don't control basically the behavior. It's basically randomly generated. This is where it becomes interesting. We have the genetic algorithm, particle sum optimization or Kokusher. So these are the type of algorithm. Basically, my study was mainly based looking at random selection, because it's, in my case, it was best to go for this type of algorithm. So what you need to understand also, most algorithms normally are based by observing the nature. As you can see, people say genetic algorithm. Normally, genetic algorithm is based on Darwin theory of human evolution. So even particle sum optimization. So all these algorithms, you can see, they are mostly nature-based. So people tend to observe how the nature evolve, how the nature function. Based on that, they will try to understand and mimic the nature behavior, and therefore create an algorithm out of it. Most of the algorithms are really based by observing the nature. So it's like we don't invent anything. So everything is based on the nature. You just use what's the nature has the best to offer. This is most of the times the case. Most of these algorithms are all based on by observing the nature. So now if we move to a typical example I've used for my study. So trying to imagine, basically, this is a typical gear shift map where you have the vehicle speed and the throttle position, and then you have different gear selection. So the way it works, when you're driving your vehicle, you press on the throttle position. So based on the vehicle speed, you will select a specific gear. So you have different type of gear here. So up to, in this case, you have up to 6 gear. So you can see when the vehicle is moving, the vehicle speed is increasing based on where you have the throttle position. You will be in a very specific gear. And that will impact, if you look at here, what we call a fuel consumption map. So the best fuel consumption point in this case will be at this point here. So what we're trying to do by manipulating the gear shift map, we're trying to move the operating point of the engine in the area where you have the best consumption in terms of fuel. So, but you cannot always do that. This is where now the constraints are coming. I will explain later on. So sometimes you cannot always push your vehicle to be at this point, because it can impact the vehicle drivability. So you can have some sludge in your vehicle and unpleasant motion in your vehicle, which you don't want. So we need to be very careful. This is where now the constraint setting is coming from. That's what I was trying to explain. The big job you have to do is to know how you can formulate a problem and set up the constraints such that you get the best of your algorithm. This is how you do things. Yeah. And then, so first of all, like I was trying to explain, the first step is to define the design variables. So the design variable in this case here will be the gear shift map position. So as you can see here, the gear shift map position will be this line here. So to define that, we've created some kind of vector of number of these different position here for each of them. So we've created so in this case, this was the downshift side and this was the upshift side. So we create different vector of 6 different variable of gear shift position. So this will be my design variable. So basically the algorithm will be changing this point. By changing this point, you will see this point will be moving on the map, and then you assess them by using a quick vehicle simulation to see how this is impacting your fuel consumption. So this is how you do it. And then from there now you can set some boundary on your design variable between plus and minus 20%. So this is just a typical example where it can be more or less. It's based on your problem specific, really. So this is how you formulate your design variable. So this is, I will call this set 1. And I believe I had at least up to 6 different variables like this. So this is how you formulate your design variable. And then the next one is select your objective function. The objective function, like I was trying to explain here, is fuel consumption and CO2 emission. That was my main target. I was trying to develop an algorithm which can optimize my CO2 emissions and also which will impact the fuel consumption. But at the same time, I needed to look at the vehicle durability. So the vehicle durability was being explained by the power, by how much power you will have when you shift the gear. So this was really important because we noticed when we were trying to reduce fuel consumption, it will having a massive impact on the durability, which was basically the power which would remain after a gear shift consumption. So this can impact your vehicle durability. So these two was kind of opposing. So that was based on these two objective function. My study was mainly based. So this is what I've used basically to find an optimal gear shift map position to be able to reduce fuel consumption, but at the same time, trying to minimize the impact on the vehicle durability. Yeah. And then, so this slide here is to explain basically genetic algorithm, the way I've used genetic algorithm trying to minimize the fuel consumption. So like I was trying to say, in reality, genetic algorithm is based on Darwin natural evolution. So which if you try to look at it, the way it works, so I've put this little human here. So you have an initial population. So the way it works, you have an initial population. Based on the initial population, you can do a recombine. So basically you will do kids, which are the offspring. And then once you have the offspring, each of the offspring will have different feature. And based on the different feature, so the way we select the Pareto, so the strongest, which will have the best feature, will go to the next generation. And the one which are not really strong, basically then will just, what we call the elitism. It's like they died, basically. So this is how it works. You basically keep that loop, reproducing, assess them, you keep the best for the next generation, and then, yeah, you keep working in that way. So this is how basically the natural evolution works when Darwin explained, and people use exactly the same concept to develop what we call today the genetic algorithm. So if I try to explain here by using the concept of the shift map, if you imagine you have an initial gear shift map, then from there we randomly create some initial population. It can be maybe 100 or 200 different population of which contain basically 200 different individual. Each of the individual, what we do, which represent a gear shift map, then we use a driving cycle. In this case was the NAD cycle, I remember. And then we have a vehicle model, which we use basically to simulate that particular gear shift map. And then once you simulate it, then you calculate the fuel consumption and also the vehicle drivability, and that will give you an initial population which you can start with for optimization. Then now, based on that, you will now go in that loop here to have an initial population where now you can start doing a recombine. So basically you will get 2 shift map, and based on the 2 shift map, you will do a combination of both. Based on the combination of both, you will get a new shift map, which we call upstream. And that upstream now, you will evaluate each of them, the CO2 emission and the drivability. And based on that, now you create a Pareto ranking. And then based on your Pareto ranking, you will select the best one, which is, you can see here, the red one here. So, and then the rest, basically, you just discard them. And then you go to the next one, and you keep running that loop up to a very specific generation you will set. It can be based on the generation, or it can be based, if you find a good solution which satisfies your needs, then you will just stop here. So this is more or less how genetic algorithm work. We use it to try to optimize the gear shift to reduce fuel consumption. And that was the main cost function I was using, CO2 emissions and vehicle drivability. Yeah. And then now I'm coming to end. So like I've explained, so this is how we use problem formulation to describe gear shift map optimization. And then the most important thing we spend a lot of time trying to formulate is really the problem formulation. That's the difficult part, really, before you can move into selecting an algorithm, which is in this case genetic algorithm. I've also used different algorithms, but that's a different topic. Genetic algorithm was one of the best, which was giving me a good solution of reducing CO2 emissions. Yeah. So that's the end of my study. If you have any question, I'm ready to take them. Thank you.
Thank you, Adama. I think that was good presentation. So anybody who has got question to Adama?
Yeah, just one question. So how did you decide the type of drive cycle you were going to use to test your solution, and how many drive cycles did you look at?
Sorry, I didn't. The first thing, I missed the first one. Can you say again? How did you
decide which drive cycle you were going to use for your optimization? So the drive cycle to test.
At this time, the main drive cycle which was dominating was NAD cycle and WLTP. Mainly NAD cycle was the one, because the vehicle homologation I was working on was mainly using NAD cycle at this time. So that's why we decided to really use NAD cycle, but we did use WLTP as well, driving cycle, to test different shift map we've developed. Yeah.
And
does that answer your question?
Did you get the opportunity to do any hardware testing for this?
Because the company I was working with was based in China. So I even had the opportunity to go to China to upload my map in different vehicles, and then we went to test them on a specific area where you test the vehicle. Yeah, we test that on the hardware side. Yeah, it was really interesting.
I guess you have to do offline first, isn't it? Because I mean, if you look at the ECU in automotive,
no,
I mean, how far are we in terms of?
You don't, basically the way it's for the optimization, you do it offline.
Yeah.
You optimize your map offline. Once you obtain your map, then you can implement the map in the vehicle and test it.
Yeah,
you don't do optimization in the vehicle. It's completely different.
Yeah,
you optimize first offline, then once you have the result, now you can go and test it in the vehicle.
Yeah, in terms of cloud computing, I mean, from the Internet of Things and all those kind of things, and the 5G coming, we have very big computing power.
Yeah.
Is it? I mean, I'm trying to see how far are we in terms of like, you could take the data from the vehicle, communicate via the cloud, send to the, to the PC in some data center, and then do the optimization, bring back the solution via cloud to the vehicle.
Yeah, you can do that. I think that's something probably people will be looking on that for now. Like the SOTA software in the air. Nowadays, people are mainly working on this because it makes things easier. So you can just quickly develop your algorithm. Once it's ready, you can ship it and do your
so because
testing. So that's something I'm sure people will be doing that. It's an area since my PhD I didn't really look at it, but I think so it's something to look at it.
Yeah, because it's really hard. For example, for the things like model predictive controller, you have all these kind of multi-shooting solvers or single shooting, wherever. They are very difficult to implement in the vehicle. So, I mean, we don't have that issue with that computing power. So you have to do offline. The sort you are mentioning at the moment is mainly to kind of update the customer software. In a sense that, you update, but I'm trying to see like in real-time communication via cloud, how far are we, how many years to wait?
No, I think it's even probably in the radar, I will say. I mean, because this was done a long time ago. So right now, I think people are thinking about the SOTA now to really, well, Tesla is doing the same now, when they developed any algorithm which they think is ready, you don't need to bring your car. They will just update it directly to you online. So this is something, people will be looking at it for this type of optimization algorithm as well, I'm pretty sure.
Yes. I think if there's no other question, maybe we jump straight away to the last topic. And our last presenter is Aikena.
Yeah, hello. I don't know if you want to stop sharing. Yeah, thank you very much for inviting me to this conference. And there seems to be a lot of PhDs here. I'm not a PhD, so it might not be really academic. Just to give you a little bit of my background, I also have a master's degree in control engineering. I've been in the automotive industry for quite a while now, so over 8 years now. I've worked on various systems. I've worked on driver assistance systems. At the moment, I work in the London Electric Vehicle Company, basically involved in the body electronics, basically, or the security, the locking, the lighting, part of the telecoms as well. So that's sort of my background. But you could be asking, how does that relate to machine learning? Machine learning is something that I got interested in recently, and I'm more or less doing a lot of research on my own spare time, basically. So I thought we could, come in and learn together, basically, just to give you an overview of what machine learning is all about and big data. Some of you have already touched on this. Dr. Umit, has talked about driver assistance, self-driving cars. Uwambe, sorry if I don't pronounce your name well. Dr. Uwambe also talked about Internet of Things, and some of these all have aspects of machine learning, basically. So if we jump straight into it. So this picture basically just gives an overview of what machine learning does, sort of the daily application. Some of us use part of machine learning in our day-to-day, but we might not necessarily know what's happening. So this picture just sort of gives you an example of, say, you're looking for Starbucks, or you're looking for a location somewhere. You come into the city and you want to find your way around, and you speak to your phone, "Hello Siri, how far is the nearest subway?" And it does a lot of processing, voice processing, does a lot, and then gives you, some audio message of what you're asking basically. So a lot of this happens at the background, and a lot of machine learning also goes through, a lot of data processing goes through at the background, so this sort of gives an overview of what it is. In terms of definition, machine learning it's a field that's been around for ages, and it's just recently picked up. So it's basically a field that allows computers to learn the hidden patterns in the data set without necessarily asking it or telling it what the rules are. You're telling it how it should do it, and then you use that knowledge to make informed prediction. So basically, you get historical data, could be labeled, unlabeled, could be structured, unstructured data. You feed it to the system, the machine. It learns the inherent relationships between the data sets and then makes a prediction. And it learns to build a model, and then from that model, you can feed it new data sets that it's never seen before, and it gives you some output, which could be a discrete value or a continuous value, depending on the problem you're trying to solve. So if you go down to the details, there are loads of different types of machine learning, algorithms, problems. From what we can see here, we see that there's supervised learning, unsupervised learning, there's reinforcement learning. Recently, with the advent of new microcontrollers, the semiconductors, we've got deep learning, which some of this has already been touched. So this picture sort of gives us an overview of the sort of problems that we could solve with machine learning. So like I said, this presentation is not necessarily going into the academics or into the algorithms, the maths behind this algorithms or this method. It's just basically to give us an overview. So when we talk about supervised learning is more to do with feeding the module, giving the system some data sets with some label. So if we look at the picture on the top right side, the labels could be, you could have a data set that's been generated from some sensors and monitors, the weather condition, the amount of rain, the amount of sunlight, different measurements, and then it uses those sensor readings to predict what the temperature could be, maybe today, maybe in a few years' time, or maybe in the next 24 hours. If you look at the downside, say you want to sell a car, you've got some vehicle you want to sell, you want to know what the price is. You don't necessarily know what it is, but you know what the engine size, the mileage, the registration year, number of past owners, number of doors, and a few other variables that you could feed in, that you could, get your hands to, and you feed it to the model. The model so the data set that you feed to the model would have various car types and the price, which makes it labeled. So you're telling it, these are the variables for this particular car, and this is how much it costs. Tons of data, feed it to the data, to the model. It sort of creates, without being programmed to do so, it understands the relationship between the input variables, and the price, such that it could generalize on a new data set. So you get a new car today, you feed it to the module, and it gives you a price. And the price is more of a continuous data type. So it's a real valued data type. It's not a categorical data per se. So regression model basically tries to minimize the the error between, say, if you have a single variable data set, you want to minimize the error between the real and the predicted, basically. So in terms of application, it could be used, for recruitment to forecast the salary. So you want to recruit someone, you've got tons of variables about the type of work they'll be doing, the number of hours they'll be spending, the number of years of experience they have, and all of those. You could use that to predict salary. For transportation, you could use that to predict estimated time of arrival for transportation. In agriculture, you could use that for, predicting the yield based on the amount of rain and all of those. So you see this happening in our day-to-day lives. So regression is all about using labeled data sets to make predictions to data points that we haven't seen before, basically. We've got a different type of supervised learning, which is more to do with classification. Now, classification is also some form of machine learning model that requires labeled data sets, but the labels are distinct values rather than continuous values. So if you look at the top right, so the top left, you have products and what the label is. So you've got orange, you've got juice, and you've got the liter size, and it tells you it's a drink. So you've got different categories. From what we can see here, we've got 3 categories: drinks, fruits, sweets. When you're building your machine learning modules, rather than using the string values as labels, you could label and code this to say the drinks represents, or 1 represents drinks, 2 represents fruits, 3 represents sweets, and so on, as many labels or categories that you have. So basically, the machine learning module also learns, using this data, what the relationship is between the products and the drinks. And then it builds a module which is trained and learns the relationship. And then when you feed it an unlabeled data set, basically all it's doing is trying to predict what that label is based on what it's learned from using your training data sets. So that's what makes it different from the regression module. It basically learns the different categories rather than giving you a particular real label, real valued output of what your unknown data is. So it could be used for sentiment analysis, for email spam classification, like we can see from the lower right, where you feed it tons of data about emails. Say the emails would have labels. Say it's a spam, not a spam, spam, not a spam, and all of those. And it builds a relationship that understands what a spam looks like and what a non-spam looks like, such that when you feed it a new email, it understands based on what it's learned from the training data set, what category the new data set is. So that's basically what classification is in a nutshell. So you could use it for image classification, text classification, sentiment analysis, document classification, movie classification, and all of those. So that's supervised learning, more or less, in a nutshell. So it's either you're doing classification or you're doing regression. But when we talk about we have yet another type of machine learning called unsupervised learning. Now, unsupervised learning is more to do with feeding it a set of data without labels. So you feed it raw data, like we can see here, and it learns to differentiate the data set by building clusters. And one of the most popular algorithms used for clustering is called K-means clustering. What it does basically is, if we look at the right side, is for this particular example, it sort of starts by randomly placing 3 centroids, which are the green circles. And then next, the objects are assigned to clusters nearest to the centroids. Then the distance between the objects, the red dots, and the centroids are averaged out to move the clusters to new locations, basically. Like you can see sort of movement happening if you look at the green dots. So the centroids are averaged out, and then the distance between the object and the centroids are averaged out and moved to a new location, resulting to a new set of cluster. And after each iteration, after going through this iteration, we each cluster basically is fed back into the loop until the centroids sort of converge, which leads us to this sort of output, basically. So it learns without being told what an apple looks like or what strawberry looks like, basically. This sort of algorithm could be used, or basically is used in customer segmentation, where you want to differentiate customers based on their preferences or what they've bought in the past, or the sort of things that they've liked, sort of content that people watch, typically on Netflix. Could be used for banking to detect fraud. In medical science, it's also used to build an algorithm that sort of says, when you see a gene looks in this, has this sort of shape, then it could be associated with this sort of disease, basically. So there are so many applications in social media, city planning, in information retrieval that you could use, clustering. Because if you have a news content, you don't know what that news content is, basically. It's hard to say if it's about football or if it's about education, basically. But what it does is it uses the content of that news article to place it within the cluster. So that's clustering in a nutshell. We also have another unsupervised learning algorithm called dimensionality reduction. It's basically when you have a lot of, so like Uwambi said, the internet of data, you have lots of devices connected together. So if you were to make certain predictions, you find out that you have lots of data inputs, and you could have multiple tons of, thousands of features for a particular problem. And the more features that you have, obviously, the more features you have, the more descriptive you have of a particular system, and the more you could do predictive modeling on that system. But the problem is, when you begin to have more features and your training data remains the same, then chances are that you run into a problem called overfitting, where your model understands more. So it sort of understands more about your training data than it does by generalizing, basically. So from what we can see in this plot to our right is basically something called the cost of dimensionality. So basically what it is as dimensionality increases, as your number of features basically increases, the classifier performance increases over time until you get to an optimal number of features, as we can see at this point. Once we get to that optimal point, further increasing the number of features basically does not yield any benefit to our model. Rather, the performance degrades. So having too many features leads to overfitting, and then the model doesn't generalize. So this is where dimensionality reduction comes into play. Basically, what it does is try to reduce dimension by selecting a candidate set of feature sets that best describes the variance in your data set. So it basically tries to map, from what we can see here, we've got a 3-dimensional data. It tries to map this 3-dimensional data set into a 2-dimensional data set whilst retaining as much information as required to describe the problem, basically. So using less features decreases the likelihood of overfitting your model. And when you have overfitting, then you're not generalizing. When you have a new data set that the model wasn't trained with, it performs less because the model understands more of your training data set than it generalizes. So some of these applications could be used to reduce the model complexity and avoid overfitting, like I've said. You could use it to derive information from a feature set to construct new feature subspace, like we can see on the top right. Applications could be, such things as when you want to compress data sets, compress the video, speed up algorithms, or use them for big data visualization. So imagine you have big data with, say, 100 features. There's no way you can visualize a 100-dimensional data set. So with dimensionality reduction techniques, we could sort of compress our data and find the most features that give us the most variance, that explains the most variance in our data set, and hence use that minimal features to perform some predictive modeling. There's another level of machine learning called reinforcement learning. So basically, it's a technique that allows an agent to interact with an environment, basically. I think this is mostly used in self-driving vehicles. So it allows an agent, in our case, it could be a network or machine learning module program, to interact with the environment by taking a set of sequence of actions in order to maximize total rewards. So each action could lead to a change in state. So how does that relate to driverless vehicle or in recommendation systems? So just to give a typical example, just take a child who is handed a TV remote control. The scenarios could basically be broken down as, say, in our own case. In this case now, the child is the agent, or we could liken it to the network or the machine learning that we're trying to train. The house and the child, the TV and the remote control is the environment. So for a vehicle, it could be the surrounding of the vehicle, the sensors and all of those that the vehicle interacts with. The state could be related to the current unaffected state of the house or the environment. So as soon as you hand the remote to the child and he begins to play with the remote, begins to understand the remote, at that point, that becomes his current state. But as soon as he starts to fiddle with the remote, start experimenting with the remote, this may lead to a new state. You know, he could change, turn on the television, or he could see nothing happen, basically. For autonomous driving, the states that we are seeing here could be the image coming in from the road ahead, the action that the agent takes could be rotating the steering wheel in a continuous range of angles. Now, how does it learn to control the vehicle? It's more like a trial and error kind of process, where if it gets a reward basically for every right action and a punishment for every wrong action. So the rewards could be that the car is on the road. It could be an integer value or something, depending on how you set it up. So if the agent steers into the right direction and the car remains along the trajectory, then it gets a positive reward. If it goes off track, it gets a negative reward. It learns over time what actions it takes that results to positive or negative rewards, and it learns over time. The core of the reinforcement learning process is something called the policy. The policy is more of a mapping between each state and the action that the agent takes in that particular state. It could be deterministic, it could be some policy that you define for each state, or it could be stochastic, where an action is taken based on some probability function. So that's more or less reinforcement learning. But if we look at the picture to the right, bottom right, and apply that to a recommendation system, say you want to recommend movie content or some product to some customer. Now the data set in that scenario could be prepared in a way that the content viewed by the user is taken as the state, current state. And then the next content that the customer or the user sees is the action. So he's taking an action to see a new movie. The reward that the machine learning, the reinforcement learning would take by recommending new content, and then the user presses and watches that content could be simulated like as the review that the customer gives to that movie, or how much interaction time he spends on that particular content. Or in the case of e-commerce, it could be what sort of review he makes on that content, or if he ends up buying that product, that could be used as the review, as the reward, and therefore the machine learning, the reinforcement learning model understands that, okay, if I recommend this sort of movies, this user either buys it or spends more time on it or not. So he uses that as a reward. So basically that's what the reinforcement learning model does. It's just more like a trial and error sort of algorithm. It's been used today on self-learning, self-driving cars. It's used in medicine today, where you have prosthetic knees to allow people walk. Everybody has different walking patterns. So what this sort of system could do is to learn how each person's walk pattern is and adapt over time. So that's reinforcement learning in a nutshell. So if we talk about big data, big data is something that's there's so many definitions, so many opinions, to big data. Fundamentally, what it is just every day we use our phones, we go online, we buy stuff, our vehicles generate, the mileage increases, we use fuel, we're spending, we're buying, topping up of fuel, going to the mechanic, we're generating data every day. We're generating data every day. So big data is basically, in a nutshell, any data that's extremely large, fast, complex, it could be structured, it could be unstructured, it could be labeled, it could be non-labeled, that cannot just be stored, using traditional methods, either in a flash drive or in a, on-premise data center. It's difficult to manage and process, using traditional method, basically. It could also be seen as a field that aims, to use the, the data set generated by all of this, technology around us, Internet of Things, to try and understand and extract meaningful insights from the data. And from what the pictures basically showing us is that all of this big data that's being generated, increasingly 80% of these are unstructured. Now, what's the difference between structured and unstructured data? Structured data sets that are more or less in a tabular form, that could go into a relational database where you have defined rows and columns, basically. For unstructured data sets, we have things like voice, video, text messages. With the advent of social media, we're generating tons of unstructured data set every day. So how do we make insights? How do we generate or utilize or analyze these data sets? Is one of the challenges with big data. Now, the question is, how big is big data? The picture to the left shows how much data is being generated by the minute. This picture is quite old, but it still gives us an idea of how much data. This is just one sector. This is just, I could say social media, basically, the amount of data being generated from social media. We've not talked about in the manufacturing, we've not talked about, in the different sectors, in agriculture, even in the underworld, lots of, things are happening all around the world. We generate tons of data set every day. And if you see the explosion, in the size of these data set, I think Kumba mentioned when he talked about semiconductors, and it was mind-boggling on how much, transistors could be put into, 1 square inch. So it's quite a lot, and how those semiconductors are able to process these tons of data set is quite fascinating. So just to give you a typical example of, so this line says that there are 500 terabytes of new data per day that are ingested in Facebook databases. That's quite a lot of data. So we can just sort of begin to get a picture of how much data is being generated on the daily, and how do we process or capture or use this data is one of the biggest challenges that companies are facing today. There's so much insight, so much information, so much value that is hidden in these data sets. Processing them and having the power to process them. These are some of the challenges that we face today. So now there are components of the certain characteristics that a data set has to meet before it can be classified as big data. This picture sort of shows, the 4 V's, as it's popularly called, of big data. So we're talking about the volume, the scale, how much data is generated, on the daily. We're talking about the variety, the types of data sets. We talked about video content, about tweets, Facebook, Amazon, healthcare, the sort of the variety of data set in different forms, in structured, unstructured, and all of those. The velocity, the analysis of streaming data, you get sensors today. Sensors are giving you values in the real time. If you go to the stock exchange, you're getting trade information happening, per minute, per second, changing by the day. The veracity, the uncertainty in the data, the quality of the data set. People don't really trust information. You need to do a lot of processing, a lot of cleaning, a lot of merging, data processing, and all of those to be able to use this data set. So when you have this component, when you have a set of data set that meets this component, then you can surely say, yes, I'm dealing with big data. But there's one V that I would say is missing in all of this, because what use is a data set if it doesn't add value to you or the business, So all of this should, or if I were to draw an arrow, I would have an arrow here going to, another circle called value, basically. So you want to be able to make business decisions with your data set, basically, which could yield profit or could be used for innovations and all of those. Now, the challenges of big data could be summarized with this 6 points. It's not limited to these, but just for the sake of this conference, I thought I'd give it a shot. So, with regards to paying off, lots of money to big data adoption projects, basically entail a lot of expenses. So if you want to opt, so you can either have on-premise solutions where you have data centers in your office place, but this comes with a lot of costs, initial investment costs, regards to getting buying hardware, new hardware, maintaining all the computers, hard drives, memories, and all of those, hiring new staffs, administrators, software developers, and all of those, and then the high electricity cost. And the problem with this is having on-premise data centers, you can't really scale. You don't have that flexibility of scaling per se as your business increases, or you could have a long investment, what we call the capital investment costs, where you want to buy, you're projecting that your business is going to increase by X percentage in the next 5 years, and then you buy tons of computer hardware, set up an infrastructure, set up a system, with the anticipation that your business is going to grow. And then in the next 5 years, something happens, say like COVID happens, and business is bad, your company doesn't grow, you've invested that much amount of money in preparation for growth, and nothing happens. So that's a lot of money tied down. So these are some of the challenges. And then you have high electricity costs and all of those. Now, if you decide to go online, cloud-based, using the cloud-based data solution, you still need to hire staff. You still need to pay cloud services. You still need big data solutions, as well as setting up and maintaining some of these, all the needed frameworks, But the good thing with the cloud computing is that it allows you to expand, allows you to scale as your business grows over time. And you only use basically what you only pay for what you use, basically. But then investing in the big data solution costs a lot of money. That's one of the challenges. If we're looking at the data quality, sooner or later, you start running into problems of data integration, since the data you need to analyze comes from different sources in a variety of different formats, and like we've seen earlier. So for instance, say you have an e-commerce business that needs to analyze data from, say, a website log or from different call centers. So you could clearly see that, there are lots of vulnerabilities, to your data. How do you process this data? How do you clean it up? How do you merge it? How do you create a big data model that could handle, this live data coming from different sources, to enable you make informed decisions? So one of the problems, trouble of upscaling also is a very big challenge, like I said, when you're expanding, trying to get infrastructure to cater for business growth. Another challenge is also a variety of big data solutions. Today we have Google Cloud, Amazon Web Services, we have Microsoft Azure, and all of those different technologies coming up, data storages, and all of those. So how do you choose which one is best for your system? Is one of the challenges that most companies facing. How do you know this is better than the other? You have to invest in a lot of professionals to come in and set up your system, capital investment upfront, and all of those, and then converting your data sets into different, getting data sets from all forms of, from all sources, from the web, from internally generated, and all of those, analyzing them, processing them to get insights. So these are all the challenges that companies face these days with regards to big data, and of course, security, which is the big thing. So big data is good, it adds value to your business, but like every other thing in life, it has its own challenges. So that's basically, in a nutshell, what big data is. The next slide basically would just gives an overview of, like Adama said when he started his presentation, you want to solve a problem using machine learning. First and foremost, you need to frame the problem. You need to look at the bigger picture. How would this be used in the grand scheme of things? What sort of problem are we trying to solve here? How do we get the data? What sort of data do we need to get? How do we clean, process these data sets? What sort of method do we want to clean them online? Do we want to create an ETL pipeline that would automate the data collection, data processing, and data visualization, and all of those? And before you start any machine learning, you need to visualize it. You need to know what your data looks like. The data set would prompt what sort of algorithm you use to solve the problem you're trying to solve from the start. So if it's a regression problem, or if it's a classification or clustering problem, so you need to visualize the data to build some understanding of what the data looks like, what the relationships are between the different features, different components of your data set. And then you prepare the data for machine learning. It could be that you want to train, validate, and test, or you want to use, say, for a time series problem. You don't necessarily need to shuffle the data set to split it into training, test, and validation. There are different techniques that you use to solve a typical time series problem. If you've got classification or regression problems, how do you handle missing data? How do you handle duplicate data sets? How do you process some of these things? And if you have strings, how do you convert those strings? Because machine learning models don't work with strings. you need to convert them to numbers. How do you understand the relationship between the strings? Is it an ordinal data set, or is it a categorical? Is it what's the word? So how do you label and code your string? So some of these things need to be, thoughts need to be put into place. And then you need to select the different models that you want to use to train. So if it's a classification program, you could use linear regression or naive-based classifiers, or n nearest, k nearest neighbors, or decision trees, or random forests, or support vector machines, basically. So you need to select different models that could help towards solving the particular problems, and then you select the best module from this candidate set of modules, and then fine-tune that model to give you best performance. And then you present your results, present the solution. The solution could be either you want to create a portal where you send to management to make a decision, say, okay, yeah, based on what you've done, they could interact with your visualization, they could interact with the model, or if it's, say, a sentiment analysis model, do you want to deploy it such that people would go in there and, get sentiments, put the text and get the results, if it's a good review or negative review, or you want to build a web application where people can go in and put the prices, the features of a house, and it tells them the price of the house. You decide on how you want to present your solution. If you want to do an Excel sheet to present your solution. So these are some of the things you have to check upfront before you start any machine learning project. And then finally, you have to launch it. And like every other system that you have running, you have to monitor it. You need to put measures on ground to monitor when your model is performing. And then if you have new data sets coming in, you can go back and retrain the model, basically updating that model over time as new data emerges, and then basically maintain the system. So this sort of gives us an overview of, an end-to-end machine learning, the different types of machine learning, the sort of applications where each of these different machine learning models are applied to. So that brings me to the end. So like I said, it's not, I'm trying not to make it very academic, but basically just to give us, an appreciation of what machine learning is. So if you've got any questions, I'm happy to answer, and we can all learn together. Thank you very much.
Thank you very much, Ikena. I think it was quite insightful presentation. So we'll take a couple of questions if you have, and then this is our final presentation for today. I feel sorry for Otmari Mwambe from Japan. I think it's almost morning now. Yeah, everybody, anyone has got a question?
Actually, I don't have a question, but I would like to say it was a nice presentation, and also this reminds me of back in the days when I used to learn a lot about machine learning, and I think now maybe it's time to go back and catch my books and start over again, just to brush my skills.
Yeah.
Yeah, it's very interesting actually.
Yeah, it is very interesting.
Yeah.
The good thing is it can be applied to almost every field, almost every sector.
Exactly.
Like from what most of you have all presented, there's an element of machine learning, in everything that you've said today. So it's such an interesting field.
Yeah, definitely.
Yes. Yeah. And actually, I mean, today what we have seen in the topic, they are kind of interconnected. and interrelated. So I think that I could say the godfather of all everything is maybe going back to the Comba JR, the semiconductors, because you wouldn't have any of these if you don't have semiconductors. So we see that the applications as well, and robotics, thermoelectrics, and of course the other three things like, let's say, machine learning and big data is also connected to self-driving car. It's also connected to the Internet of Things. And also, I mean, optimization, also you need optimization in all of these systems as well. So the gear shifting mapping and maximum power point tracker. So I think, yeah, that was good discussion. So, and I would like to thank everyone for your support, for the listeners, for presenters. I think it was quite good. I mean, we need to team up and share the knowledge. That's the key idea of this forum, is knowledge sharing and knowledge transfer. I've learned something today. So I'm sure other people have learned from other people as well. And again, yeah, I would say like officially we have closed the meeting.